Hello, hello. Good morning, good morning. Mic check, check, mic check. Good morning, good morning. Welcome one and all, welcome one and all. Check, 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 check.
ಚೆಕ್ ಚೆಕ್ ಮೈಕ್ ಟೆಸ್ಟಿಂಗ್. ರಾಘವೇಂದ್ರ, ಹಲೋ. ಆದಿತ್ಯ ರಾಘವೇಂದ್ರ ಇದ್ದಾರಾ? ಹಲೋ, ಟೆಸ್ಟಿಂಗ್ ಟೆಸ್ಟಿಂಗ್ 1 2 3 ಚೆಕ್.
श्री गणनाथुनी शारद सत्कबुलनु श्री गणनाथुनी शारद सत्कबुलनु सहज योगी मुनुलन सुरुलन देव ब्राह्मणयुनि सकलांतर्यामी हरिणी चाल भजिन्तुं रामय्य
ಕಟ್ಟಿದರು ಕಟ್ಟಿಸಿದ ಸಾಮ್ರಾಜ್ಯ
ದೀಪದೊಳು ಪ್ರದೀಪಗಳ ಸಂಖ್ಯಾತ ಕಿರಣಗಳು ಎಲ್ಲೆಡೆ ಹೊರಹೊಮ್ಮಿವೆ ಜಯವೆನ್ನುವ ಈ ಸಂಸ್ಥಾನಕ್ಕೆ.
Chairman and Dr. Sitaram, Vice Chairman of the Kokula Education Foundation, for their invaluable support in the conducting Icamst in cooperation between with KMUTNB. Dr. Malini Sisiyanan, who is attending this conference on behalf of King Mongkut University of North Bangkok. I congratulated Dr. Naidu, Principal of Lamia Institution of Technologies, and the organizing secretaries, Dr. Madhu from IIT,
We request all the participants to please occupy the front rows. Please move to the center. All the participants are requested to please occupy the center row.
Mic check. Mic check. Mic check. How are you, Raghavendra?
They want more. Yeah, please, we request you to occupy the center row. Please, you also can occupy the center.
Hello, hello, hello. Hello, hello. Hello, 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 hello. Hello, 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 hello. Test, 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 test. One, 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 one. Yes, hello, hello. ನಾನೇ ಮಾತಾಡಿದ್ದು ಸರ್ ಅದರ ಹಲೋ 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 ಹಲೋ
ತುಂಬಾ ಜನ ಬಂದಿದ್ದಾರೆ ನನ್ನ ನೋಡೋದಕ್ಕೆ.
the last rows, can you please come in the front? People who are sitting in the last rows, requesting you to come to the front. The left corner, hello, please come to the front.
Good morning, all. I request all the guests to be please seated. Good morning, all. The guests will be arriving shortly. So I request all the audience to please switch off their mobiles or keep the mobiles on the silent mode. My request to all the audience, please keep your mobiles on the silent mode. The guests have just arrived. Good morning to all who have joined us today for the inauguration of the International Conference on Advanced Materials for Sustainable Technologies, ICAMST 2024. With the blessings of the Almighty and our late founder, Dr. M.S. Ramaiah, today, M.S. Ramaiah Institute of Technology stands as a premier institute in the landscape of technical education, and as a part of our ongoing collaborative initiatives, we are inaugurating this international conference in partnership with King Mongkut's University of Technology, Bangkok. With this, I now invite all the dignitaries on the dais. I request Principal and Vice Principal, sir, to please escort the dignitaries to the dais. I now request all to please rise for the Ramaiah anthem.
सकलान्तर्यामी हरिणी चाल भजिन्तुम्
ज्ञानं विज्ञानं च भक्तिसहितम्
भूषण
ईरामय्य समूह संस्थान
ज्ञान विज्ञान विद्या विनय भूषण ईरामय्य समूह संस्थान तारे विहारिते आगले ई मालिके जयवेन्नुव ई संस्थानके द्रष्टाररु ಕಟ್ಟಿದ ಕನಸಿನ ಸಾಮ್ರಾಜ್ಯವಿದು
ದೀಪದೊಳು ಪ್ರದೀಪಗಳ ಬೆಳಗುವ ಶ್ರದ್ಧಾ ಸ್ಥಾನವಿದು
ಅರಿವಿನ ದಿಗಂತದಾಚೆಗೆ ಜಿಗಿಯುವ ಸಂಪನ್ಮೂಲವಿದು ಗೃಹ ಗೃಹದಲ್ಲಿ ಗೃಹ ನಿರ್ಮಾಣಪರಿ ತಂತ್ರಜ್ಞಾನದ ಸೋಪಾನವಿದು ಅಮಿತ ಜ್ಞಾನಕ್ಕೆ ಸಾಧನ ಕ್ಷೇತ್ರವಿದು ಪ್ರತಿಭೆಯ ಸಾಧನೆ ಮಾಡಲು ಸ್ಫೂರ್ತಿಯ ಕೇಂದ್ರವಿದು ಅಜ್ಞಾನದ ಕತ್ತಲೆ ನೀಗುವ ಸುಜ್ಞಾನದ ಸೂರ್ಯನ ರಶ್ಮಿದು
ಜಗದೋದ್ಧಾರದ ಹೊಂಗರಸಲು ಹತ್ತಿರ ಅರಿವಿನ ತಾಣವಿದು
ಅರಿವಿನ ಹರತೆಯು ಬೆಳಕನ್ನು ಚೆಲ್ಲಿದೆ ಅಸಂಖ್ಯಾತ ಕಿರಣಗಳು ಎಲ್ಲೆಡೆ ಹೊರಹೊಮ್ಮಿವೆ ಜಯವೆನ್ನುವ ಈ ಸಂಸ್ಥಾನಕ್ಕೆ
Thank you all. I now request Dr. N.V.R. Naidu, Principal, Ramaiah Institute of Technology, to please deliver the welcome address.
A very good morning to you all. Bowing to the lotus feet of our beloved founder chairman, Dr. M.S. Ramaiah, who is blessing all of us from heaven. I am taking this privilege of welcoming all of you on behalf of Rama Institute of Technology to the inaugural function of the International Conference on Advanced Materials for Sustainable Technologies, jointly organized by the Departments of Biotechnology, Chemical Engineering, Civil Engineering, Industrial Engineering, Mechanical Engineering, Electrical, Physics and Chemistry of Rama Institute of Technology, Bangalore, and King Mongkut's University of Technology, North Bangkok, Thailand. This conference would be an excellent opportunity for all the international and national scientists, professors, students, and industrialists to learn about recent achievements in materials science, microscopy, engineering, technology, and energy. This event features a variety of lectures by renowned scholars and specialists, including keynote speakers and special sessions on a wide range of topics. At this juncture, I would like to brief about Rama Institute of Technology. The RIT, established in the year 1962 by our founder chairman, Dr. M.S. Ramaya, a great philanthropist, visionary, industrialist, and educationist. The journey of the institute began in the year 1962 with two engineering programs, mechanical and electrical. Over time, it has expanded significantly and now offers 18 undergraduate programs and 13 postgraduate programs, and all the 18 departments are recognized as an R&D centers affiliated to the Visvesvaraya Technological University, Belgavi. In the year 2021-22, the institute has introduced a full-time PhD program with the Ramaya Doctoral Fellowship, providing a monthly stipend of Rs 25,000. It is my privilege to share a few important achievements of our institution. Celebrated the Diamond Jubilee of Rama Institute of Technology on October 16, 2022. Centenary birth celebrations of our founder chairman, Dr. M.S. Ramaya, on 1st March 2023. All the eligible UG and PG programs have been accredited by NBA since 2001. The institute has continuously ranked among the top 100 engineering colleges across India as per the National Institutional Ranking Framework, Minister of Education, Government of India, since the inception of NIRF, and in the year 2024 secured 75th rank under the engineering category out of 1,463 engineering institutions, and number one across the VTU. Number one across the VTU affiliated institutions in Karnataka, and also 21st rank in the architecture category out of 115 schools of architecture across India. This is also number one across the VTU affiliated institutions. To promote multidisciplinary research, Institute has established 6 centers of excellence. And regarding the King Mongkut's University of Technology, North Bangkok, is a leading technological university in Thailand. In 2007, King Mongkut's Institute of Technology, North Bangkok, was renamed as the King Mongkut's University of Technology, North Bangkok, and became an autonomous state university. Now, it is my privilege to welcome and introduce the today's distinguished chief guest, Dr. Tarun Sauradeep. Dr. Sauradeep assumed the charge as a director, Raman Research Institute, on 20th January 2022. Before coming to Raman Research Institute, he was a professor and the chair of the physics department at the Indian Institute of Science, Education and Research in Pune. Dr. Sauradeep is an expert in cosmology, gravitational wave physics, and astronomy. He has made significant contributions and established a strong Indian effort to address difficulties comparable to international research. Dr. Sauradeep is a recipient of various awards and fellowships. To mention a few, Fellow of International Society on General Relativity and Gravitation in the year 2013, Fellow of the Indian Academy of Sciences, Bangalore in the year 2013, Fellow of the National Academy of Sciences, India 2018, Grover Cosmology Prize 2018, Grover Foundation, Hariom Prerit Vikram Saurabhai Research Award for Space Science. Degree, please to join. and introduce the other chief guest, Dr. Malini S., Associate Professor and Assistant to the President for University of Internalization Strategies and Special Affairs, King Mongkut's University of Technology, North Bangkok, Thailand. Dr. Malinis received her PhD in plant pathology from the University of California, Davis, USA in the year 2011. Dr. Malinis' research interests are in the biorefinery, biomass, and biocomposite materials. She has been the principal investigator and co-investigator for more than 90 research projects supported by the government and industrial sectors in Thailand and other countries with a value of more than 3.5 million US dollars. She has supervised and co-supervised more than 70 students, published more than 160 reviewed journal articles and 20 book chapters, participated as a presenter, plenary speaker, and the invited speaker in more than 120 international conferences. I welcome you, madam. Now I request our Honorable Secretary, GF, and Director RIT, CMR Ramaya sir, to welcome and felicitate Dr. Malini. I request other dignitaries also join. On this occasion, I am very pleased to welcome our beloved Honorable Vice Chairman, Gokula Education Foundation and Director RIT, Dr. M.R. Sitaram sir, former Cabinet Minister, Government of Karnataka, and currently the member of the Legislative Council, Government of Karnataka. He has always emphasized the need to improve education quality to satisfy all the stakeholders. He has initiated many development changes in the college administration, thereby improving the amenities on the college campus. He gives equal importance to the employees' personal development by creating opportunities suitable to their capabilities. He is a leader for excellence, guiding all of us constantly to achieve academic and professional excellence. Under his able guidance and dynamic leadership, MSRIT is consolidating its position as a leading technological institution of international repute. He is very well known for his kindness and social service. I am very delighted to inform you all that our Honorable Vice Chairman, Dr. M.R. Sitaram sir's passion and commitment to education and society have been recognized by the University of Mysore and conferred the honorary doctorate in literature on 3rd March 2024. I welcome you, sir. I request Vice Principal to welcome you. Thank you, sir. We are honored to have our Honorable Secretary, Gokula Education Foundation and Director, RIT, Sri M.R. Ramaya sir, as a guiding force in all our activities. He is not only the compassionate, but also kind-hearted, always providing us with affectionate guidance. He is an efficient and effective administrator. Sir, personally, I pay my respects and welcome you to this function. I welcome you, sir. I request that Archana, madam. I'm very happy to welcome our Chief Executive GEF, Engineering and General Sciences, to Dr. Parswanath HV, retired IAS, a strong professional with a PhD focused on aerobiology. I welcome you, sir. It is my privilege to welcome our Chief Academic Advisor, GF Engineering and General Sciences, Dr. Karisiddappa, former Vice Chancellor of VTU, Belgavi, to this occasion. I welcome you, sir. I welcome Professor G. Ramchandra, Chief Finance Officer. I welcome the Vice Principal, Dr. Pradeep Kumar Dishit, and Dr. Archana, and Dr. Madhu is the coordinator and as well as the organizing secretary of this international conference. I also welcome the Professor Gaurav Manik, head of the Department of Polymer and Process Engineering, IIT Roorkee, Dr. Sunny Jafar, Associate Professor of Mechanical Engineering, IIT, and Dr. Joshish Kumar P., Director, Sophisticated Testing and Instrumentation Center, Alliance University, to this function. I hereby welcome all the session chairs, authors, delegates, research scholars, and other invitees to this conference. I am sure all the participants will have a very fruitful and informative deliberations and a comfortable stay during these 2 days of the conference. I hereby welcome the Registrar Admin, all our HODs, faculty, staff, organizers of this conference, students, and volunteers of this conference. Once again, welcome one and all. And I welcome all the media and IT personnel come here to cover the proceedings of this inaugural function. Thank you one and all.
Thank you, sir. I now request our stage committee people to please welcome our principal, Dr. N.V.R. Naidu. In the Indian culture, it is a traditional ritual to light a lamp before beginning any auspicious event. This invokes divine blessings, creates positivity, dispelling all the darkness. I request all the dignitaries to please light the lamp. Thank you all. I request our stage committee to also welcome the organizing team led by Dr. G.M. Madhu, Dr. Kottam, and Dr. Anil. I now call upon Dr. G.M. Madhu, the organizing secretary of the conference, to brief about the conference.
A very good morning to all. The esteemed chief guest of the today's function, Dr. Tarun Sauradeep, the director of Raman Research Institute, Bangalore, Dr. Malini Shirianu, the assistant to the president of the University of International Strategies and Special Affairs, King Mahmood's University of Technology, North Bangkok. The president of the today's function, Dr. M.R. Sitaram sir, Honorable Vice Chairman of the Gokul Education Foundation, Director of Ramaya Institute of Technology, and Member of Legislative Council, Government of Karnataka. Guest of honor for the today's function, Sri M.R. Ramaya sir, Honorable Secretary of the Gokul Education Foundation, Director of Ramaya Institute of Technology, Dr. Karisidappa, Chief Academic Advisor to GEF, Dr. Parasuna, Chief Executive of the GEF, Sri Ramchandra sir, Chief Finance Officer, Dr. N.V. Naidu, Principal of Ramaya Institute of Technology, Vice Principal, registered distinguished plenary speakers, participants, research scholars, and my dear colleagues. I am honored to stand before you to present a brief report on the International Conference on Advanced Materials for the Sustainable Technologies, Icamst 2024. This conference is jointly organized by the Ramaya Institute of Technology, Bangalore, and King Mangots University of Technology, North Bangkok. This conference is mainly organized by Department of Mechanical Engineering, Chemical, Civil, IEM, Biotechnology, Physics and Chemistry Department of the Ramaya Institute of Technology. This conference marks a significant step in our quest to advance our research in the field of sustainable technologies. Icamst 2024 was convinced with a vision of establishing robust research collaboration between the two esteemed institutions. It is a testament for the commitment of both Ramaya Institute of Technology and King Mangots University of Technology to advance in the frontier knowledge and foster our international partnerships. We received around a total of 200 research papers across the globe and reflecting the broad and growing interest in the sustainable materials. After thorough review, only 152 papers were selected for the final presentation at the conference. These papers represent a diverse array of research topics, each contributing the valuable insight into the advanced materials and their applications in the sustainable technologies. Over the course of 2 days, Icamst provides a dynamic platform for the researchers to exchange knowledge, engage in meaningful discussions in the recent advancements, and explore the potential collaborations. This conference covers a wide range of topics related to advanced materials for the sustainable technologies, showing the latest research innovation in the critical field. We are privileged to have received a contribution both international and national researchers. We have received around 30 international papers and many are from the King Mangots University, and we have Indonesia, Bangkok, and many other countries. Because of our short schedule, we have made many of the international papers on the online mode. We have a keynote address to be delivered after this inauguration by Dr. Malini, and a plenary talk one by Gaurav Manik from IIT Roorkee. Plenary talk 2 will be delivered by Sunny Zafar from IIT Mandi, and plenary talk 3 will be delivered by Dr. Jyotish Kumar of Alliance University. This conference featured 12 parallel sessions, including 2 will be held online to accommodate the wider audience, as I mentioned. And thanks to all the collaborative efforts which are involved in conducting this conference, we had laid this groundwork for the future research collaboration between the two universities and to have a foster vibrant exchange of ideas and undoubtedly to drive the progress in the sustainable technologies. I must thank the president of KMTUBNB, that is King Mangots University of Technology, Dr. Suchara Saichin, Dr. Sanjay M.R., the senior research scientist and associate professor advisor within the office of the president university for the promotion and development towards these international goals. And my colleagues, Dr. Nagaraj Kottam, Dr. Anil, the joint secretaries of Icamst, for their great hard work in organizing this conference. Thank you all the distinguished guests, speakers, participants, organizing team of your institution and support. We look forward for continuing this collaborative effort toward the sustainable technologies and building a stronger research work. All the sessions will be available online in the YouTube session. Thank you.
Thank you, Dr. Madhu, for providing an overview of the multitude technical sessions which will be offering a platform for knowledge exchange accompanied by expert plenary sessions spread over 2 days. I now request our honorable chief guest, Professor Tarun Sauradip, to please release the souvenir of the conference and the other dignitaries to please join. Thank you all. It's now time to have the inaugural address by our chief guest, Professor Tarun Sauradeep.
Good morning. Let me begin by thanking you for the warm welcome. I'm deeply honored to be present amongst such august company on the dais. I extend my warm greetings to Dr. Malini Sriarionun, King Mongkut University of Technology, Thailand. I'm doing this welcome just to welcome you to India on behalf of the scientific community of India. I'm sure you have been welcomed here by others. Dr. Sitaraman, Sri M.R. Ramaiah, Dr. M.R. Jayaraman from the Gokula Education Foundation, and other distinguished members. So let me begin again by thanking Dr. Naidu for the kind invitation to be the chief guest at this event. And also, let me extend my warm greetings to all the leading researchers, young scientists, postdoctoral, and research scholars who have traveled to this conference and are in the audience. So I think it's a unique opportunity, and I'm really glad that there's this opportunity to possibly make another connection between two institutions of eminence led by people who are very, very personalities who have been very, very well known in the national stage and also international. So I come from the Raman Research Institute, which is also institute that completed 75 years in the past couple of years, and set up by Professor C.V. Raman. And of course, here, Dr. M.S. Ramaiah's institutions as an educationalist is very well known in the country, and I'm glad to have this opportunity to come here and be a part of one of the events. I think it's a very critical need in the nation as scientists and educationalists to realize that we need science and scientific research to happen in the presence of young students. Of course, we have institutions which have research happening with the brightest young students, but we also have institutions such as the Raman Research Institute, where we dearly miss young undergraduates. And you can't revamp the whole thing, but what we can do is certainly to create strong bridges of cooperation where our scientists, I'm sure, at Raman Research Institute, who been working on frontier sciences, doing very well, could have more well-defined opportunities to have interns from institutions and students here. We could also have research collaboration. I'm aware that some of that is happening, but I think this is a great opportunity for research institution and institution which is producing young people in technology and sciences to come together. The theme for the conference is, of course, a word that is now being recognized as a very important word, sustainable development. We have realized that while science has taken us immensely far in our capabilities to tame nature, eventually nature is much, much more complex, much, much more powerful, and we need to heed to how you do development of science and technology, how you translate that in consonance so that you don't, for your own good, not upset the rhythm of nature to a great extent. So advanced materials, of course, is one way to address that, and I'm sure the deliberations of the conference will lead to new ideas and more progress in this very, very critical area. So this is, of course, a problem that is widely recognized on many fronts. I think every young person is being brought up with this awareness that we are, stepping towards global warming. We have climate change as an issue, and even, things which look remote. Say a few decades back, we started going to space, but now the space debris itself, calls for sustainable exploitation of the space. You want, of course, all your, internet connectivity, everything to happen, satellite connectivity, but it comes at a price. And it is very important to, and these are right in the lap of the scientists and technologists to find an answer to how do we do this all, but make sure that we can keep doing it and not be, limited by what we have done and what we have left behind. So I also really wanted to point to, attention to alternate sources of energy. A couple of weeks back, Dr. Kakotkar came and delivered a lecture at the Raman Research Institute. We have a Science and Society series. And he pointed to the fact that for a country like India, simple numbers show you that we need to really rethink how we want to meet our energy goals if we want to get anywhere close to what is being called Viksit Bharat. It's a name, but we all know how to quantify that in some sense. We know how much energy need a developed society would have. So I think we have a lot of scope for development. Fundamental research that is done at our institute often also, presses us to develop materials, technology that are at the frontiers, and at that time it is probably to solve one problem that we are looking at for science, but they usually spin off to many other applications. So I know some of my colleagues are struggling to find RF shields for the space mission that they are going to send, which is light, and they're exploring all kinds of material because these things start limiting what you can do. So I again warmly thank the organizers for giving me this opportunity to come to this gathering and address you. And I wish the conference and the organizers here all the best for the conference, and again the partnering university from Bangkok for the partnership that we see between the countries. Thank you so much.
Thank you, sir, for your address to our audience here about conducting research by involving undergrad students for translating science and technology. I thank you for this. We now have a message from Dr. Habil Suchart, who is the president of King Mongkut's University of Technology, an outstanding researcher with more than 160 publications with an H index of 75.
Dear ladies and gentlemen, it is given my immense pleasure to address you all at the International Conference on Advanced Materials for the Sustainable Technologies, Icamst. This is significant event is organized in cooperation between King Mongkut University of North Bangkok, Thailand, and the Lamaya Institution of Technology, Bangalore, India. I am delighted that we are conducting this conference in partnerships with RIT Bangalore, marking the beginning of the promising collaboration with RIT. This conference presents an excellent opportunity for delighted and degraded from various universities and institutions to interact with world-class scientists and discuss with the current status and recent developments in these critical fields. I would like to express my thanks to Dr. Jayaram, Chairman, and Dr. Sitaram, Vice Chairman of the Gokula Education Foundation for their invaluable support in the conducting Icamst in cooperation between with KMUTNB. Dr. Malini Sisiyanan, who is attending this conference on behalf of King Mongkut University of North Bangkok. I congratulated Dr. Naidu, Principal of Lama Institution of Technologies, and the organizing secretaries, Dr. Madhu from IIT and Dr. Sanjay Lankappa from KMUTNB for their coordination and effort in organizing this conference. I am very happy to extend all possibility support on behalf of King Mongkut University of North Bangkok for future cooperation in various areas of research with Lama Institution of Technology. I wish Icamst a grand success. Looking forward to all future cooperation. Thank you very much.
So I request Dr. Malini to please convey our thanks to Dr. Habil for his message. I now call upon Professor Malini, who heads the International Relations of King Mongkut's University of Technology and has contributions in the area of biorefinery and biocomposite materials, for her address.
Dear distinguished guests, professor, colleague, and student, good morning. My name is Malini Sirayanan. As a representative of King Mongkut University of Technologies North Bangkok, or KMUTNB, today it is the great pleasure for me that I have been invited to join this conference, and I'm happy to express my congratulations to the success of this event on the material engineering, science and technologies in Icamst 2024. As we gather here, we are united by a shared commitment to pushing the barrier of science, engineering and technologies, and to explore the fascinating world of materials, which are very foundation of human living every day. Material science and technologies is more than just a field of studies. It is the backbone of innovation from the earliest days of human civilization to the present day, our daily life, where advanced composites of materials and nanomaterials are leading revolutions in industry, ranging from fundamental things, our daily life, in food, in essence of life, in medicines, to aerospace. This has been at the heart of human progress and civilization. The challenge that we have nowadays is engaged in the climate change, resource scarcities, and the ever-growing demand of the society to looking for the more sustainable, efficient, and high-performance materials. These activities require not only basic scientific mind, but also the collaborative spirits of our researcher, professor, and student. to transcend our finding to the application. So this conference will be the best platform for the idea from professor, researcher, and student to gather together to exchange, to create the new innovation and showcase our finding to the world. And partnership will be initiated in this event. I would like to extend my heartfelt thanks to everyone who attend this event, and especially the committee who are very important to make this conference success. From the organizers, sponsors, speakers, and attendees, especially Professor Jayaram, the conference chairman, Professor Satiram, Professor Ramaya, Professor Ramaprasad, Professor Ramachandra, our vice chairman, as well as Professor Naidu, who is the major organizer who inviting me and KMU TNB to collaborate in this event. So I wish you all have a productive and inspiring conference. May the discussion we have today and tomorrow will be the groundwork of our innovation for tomorrow. Thank you everyone and congratulations.
Thank you, Dr. Malini, for providing insights onto the ever-increasing demand of sustainable materials. Thank you, ma'am. I now request our Chief Academic Advisor, Dr. Kari Siddhappa, to please address the audience.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. Good morning. The chief guest of today's program and the director of Raman Research Institute, Professor Tarun Sarupji, the president of this program and honorable vice chairman and the director of RIT, Dr. M.R. Sitaram sir, honorable treasurer of GEF, Sri M.R. Ramaya sir. On the dais we have Dr. Professor Malini S. from KMU North, Bangkok, Professor Parshanath ji, Professor N.V.R. Naidu, the Vice Principal, Dr. Dikshit, the coordinators of this program, Dr. Sanjay, Dr. Madhu, two keynote speakers from IITs, Professor Gaurav Manik from IIT Roorkee, my alma mater, Dr. Sunny Jafar from IIT Mandi, our Chief of Finance, Ramachandra, the members of the faculty, deans, registrars, invitees, my dear student friends, ladies and gentlemen, press and media. I am very delighted to be part of this inaugural program. At the outset, I seek the blessings of Dr. M.R. Ramaya for blessing us with a great institution and such kind of a vision in early 60s. Friends, International Conference on Advanced Material for Sustainable Technology, a very prominent area, and one can understand the importance of this conference looking at the group involved. We have team from science departments, we have team from technology departments and engineering departments, of course in association with KMU. The novel materials are playing a very important role in each and every day activity of ours. And sustainability is another area wherein we need to look for these novel materials which are have less impact on environmental conditions. That is one of the biggest challenge the whole globe is facing. The novel materials, in the sense that not only we try to innovate new materials, we must also concentrate on recycling of the materials and the reuse of the various materials which are otherwise unfriendly to environment. The naturally available materials or the natural resources are becoming remote. And this society is highly energy conserving or intensive society. We depend on lot many materials, lot many innovative materials which are highly energy intensive. To produce a gram of material, we need to use so many kilowatts of energy. So that is why a conference like this will have to be thought carefully in terms of nature-friendly, reusable, recycling materials, which will otherwise do not impact the environment so badly, which is very, very critical. Every day we have problems, we have health issues, we have shortage of many naturally available materials, including water and minerals. So therefore, this conference will really talk on those kind of steps to be initiated by the research organizations and the society to use the minimal material and get the wonderful benefits. In this context, the bioelectronics has come to our rescue. Many innovations and research which are happening in bioelectronics have produced very wonderful, innovative, nature-friendly materials. I think some of the topics which are included in the conference proceedings are very interesting. So definitely they will produce material which is very useful to the mankind and which will be used by society with less impact on the environment. So with these few words, I congratulate the principal and all the organizers and the team from MKU for conceiving this idea of a very relevant topic, and definitely the participants will have many good takeaways, and also they will enjoy the hospitality of Ramaya group of institutions. Once again, I thank you all for hearing me, and congratulations to all the participants and the organizers for this wonderful conference. Thank you very much.
Thank you, sir. I think sir has emphasized on materials which are made with low carbon footprint and are recyclable, reusable. Hope we address this issue in the 2 days. And I think the update is very much presented in the proceedings. I now call our Chief Executive, Dr. Parswanath HV, to please address the gathering.
Distinguished guests of today's morning session, and also the chief guest who just inaugurated inaugural addresses, 2 keynote addresses by our Dr. Tarun Sauradeep, Director of our Raman Research Institute, and Dr. Malini. They have thrown a lot of light on their speeches regarding the 2-day workshop which we are going to have. And we also have our respected Vice Chairman Dr. Emma Sitaraman and Mr. Emma Ramaya, who are kind enough to attend this and beside this program. And we have our distinguished other members of this organization, and also our academic advisor who just addressed his speech now. Just to tell, today we have a very important topic for discussion and also for seminar. At the same time, I also forgotten that we have distinguished invitees from the IITs, Rookie, and also other institutions who are here to address us in the various sessions with us, and also very other eminent scientists who have come from different parts of the country to participate in this session for the next next 2 days. So at the outset, I think this today's conference is been titled as Advances in the Advanced Materials. To tell you frankly, whatever the materials which we have used so far, so what is that we are doing in advance for this advanced materials? So, life in this current 21st century cannot be depending on the limited groups of materials. Instead, we depend on unlimited number of materials for our sustenance. So in the absence of this, for example, it is dependent on unlimited materials and advanced materials, which includes, for example, the advanced materials, laptops, computers, and various technologies which we are adopting. So all these are advanced technologies we adopt just for our proper use and sustenance of the whole system in the planet. Finally, just to tell what exactly is the advantages of this seminar. What is why we have called this seminar? What are the things we should get out of this seminar? So to tell you very briefly, I think this has a lot of advantages to us. This advanced materials. What is advanced materials means? General benefits of advanced industrial materials are several and they have a potential of bringing cheaper, more sophisticated, and more user-friendly products. Hence, household items and personal vehicles and so many other durables are already improving because of the quality of our life, hence saving the labor. So all this is all due to our advanced materials. I think I need not tell all I think we will have a very detailed seminar for the next 2 days. Finally, just to sum up the whole thing, I should simply say that this workshop especially will have one of the greatest emerging benefits of this advanced material will be improvement in our most basic needs of good health, then society. The 20th century delivered a revolution in medical care and disease becoming preventable or curable, and more previously fatal and injurious becoming treatable than during any other period. So, in any other period of the history, the next 2 decades will hopefully surpass these previous innovations on every occasion and will increase inconceivable levels, so and it will help the society. So finally, to tell you, the combination of this new advanced material technology and including inorganic advances and tiny AI-driven and various other things will going to help us in a big way. I think this is too much a technical topic for us. So I think these next 2-day sessions we will have a detailed discussion, and you will come out with various types of recommendations which will be suitable to our institutions, societies at large. And with this brief words, I want to conclude my speech. Thank you, one and all. Thank you.
Thank you, sir, for your insightful comments. I now request our Honorable Vice Chairman and Director of MS Rama Institute of Technology, Dr. M.R. Sitaram, to please address the audience present here.
Morning, everybody. Bowing before Almighty God and our Honorable Founder, Chairman, and my beloved father, Dr. M.S. Ramaya. I, on behalf of the Gokula Education Foundation, welcome all the distinguished guests, delegates, the media for this prestigious international conference on advanced materials for sustainable technology. The chief guests of this August International Conference, Dr. Tarun Sauradeep, he's the director of the neighboring Raman Research Institute. Welcome you, sir. And he's already delivered his inaugural address. And Dr. Malini, who's the assistant to the president for University Internationalization Strategies and Special Affairs, King Mongkut's University of Technology, Thailand. Welcome, Iman. Shri M.R. Ramaya, the Secretary of our Gokula Education Foundation. Dr. Parasranath, our Chief Executive. Shri Dr. Karisiddappa, our Chief Academic Advisor. Our Chief of Finance, Mr. Ramchandra. Dr. N.V.R. Naidu, our respected Principal. Dikshit, the Coordinator, Shri Madhu, and all the HODs, and the distinguished speakers who have come from IIT, Roorkee, and other institutions. This is a conference which is going to exchange amongst yourselves the various composites of materials which you are going to see that mankind, the industry, benefits from this. I, as an entrepreneur, just after graduating, I also then, 1987, 88, I had also thought about this epoxy resin industry to make the mission beds for the CNC machines and all that. You know, this lathes and machines used to have huge castings. They used to be very heavy. And then I tied up with a MOU with Studer of Germany. They are the pioneers in epoxy resins, mission bed technology in the world. Of course, it was very, very early and I was thinking too far ahead. Now these things have all emerged and are running today. But these epoxy resins, which started in the 80s, to reduce the weight of inherent machines which, because generally Germany is a place where industrial revolution took place. They are the people who manufactured the best of the CNC machines and other machines in this world. And I had taken about 2 weeks' time in that Studer Institute. And after I came back and started setting it up, my late father called me and said, no, enough of this industry, please come and join me in the college. So that is how my entrepreneurship in polymers and emerging advanced materials ended. However, the world has moved on, and today we are really delighted that 200 plus delegates have come here. You have participated, you are now participating in this international conference. And I think in the next 2 days of 3 sessions you'll be having now. So this will be a great insight into your own experience and your own benefit for the industry, for society, and for institutions like Mongkut University and Ramaya Institute of Technology in large. So we as founders, my father who was the founder of this institute, we always have been trying to impart quality technical education to the people of this country and the students who pursue education here. So this is one step where the Gokula Education Foundation supports this initiative to conduct this international conference. I wish the chief guest and the main speakers, keynote speakers and the other speakers who have come from the IITs will throw more light on the emerging sustainable materials which is going to be helpful to humanity. And once again, I wish this international conference all the success, and may all the delegates gain a lot from this conference. Thank you.
Thank you, sir. You've been always motivational and inspiring to our faculty and students, and hope we always work together and come towards improving the quality of research at the institution. As we move towards the end of the inaugural session, I call upon Dr. Pradeep Kumar Dikshit, Vice Principal, MS Rama Institute of Technology, to propose the vote of thanks.
Good afternoon to all the dignitaries on and off the dais, HODs, faculty, staff, invitees, and delegates present here. On behalf of Ramaya Institute of Technology, I would like to express my gratitude and propose a vote of thanks. I would like to extend my sincere appreciation to our esteemed chief guest, Dr. Tarun Saurdeep, Director, Raman Research Institute, Bangalore, for taking time for his busy schedule to be here and for enlightening us with his inspiring words. Thank you, sir, for gracing the occasion. My sincere thanks to Chief Guest, Dr. Malini S., Assistant to the President for University Internationalization Strategies and Special Affairs, King Mongtus University of Technology, North Bangkok, Thailand, for sharing her rich experiences and motivating words. Thank you, Madam. My heartfelt gratitude to Dr. M.R. Sitaram, sir, our Honorable Vice Chairman, GEF, Director, Ramaya Institute of Technology, and Member of Legislative Council, Government of Karnataka, for his continuous support, encouragement in all our activities, and for the presidential address. Thank you, sir. My sincere thanks to our Honorable Secretary, GF, and Director, RIT, Sri M.R. Ramaya, sir, for his guidance and gracing the occasion. Thank you, sir. I extend my gratitude to Dr. Paswanath H.V., Chief Executive, GF Engineering and General Science, for gracing the function and addressing the granting. Thank you, sir. I extend my sincere thanks to Dr. Karisida sir, Chief Academic Advisor, GF Engineering and General Science, for gracing the occasion and addressing the gathering. Thank you, sir. I would like to express my gratitude to Dr. Anivya Naidu, sir, Principal, RIT, and Conference Chair, for always inspiring us and being a pillar of strength in all the activities. Thank you, sir. Special thanks to Dr. G.M. Madhu, Head Department of Chemical Engineering and Organizing Secretary of this conference, for all his efforts in making the event a grand success. Thank you. Thanks to Dr. Archana, Registrar Academic, RIT, and Conference Co-Chair, for her constant support and involvement in all the activities. Thank you, Madam. Thanks to Sri G. Ramchandra, Chief of Finance, GF Engineering and General Science, for gracing the occasion. Our sincere thanks to authorities of King Mongtus University of Technology, North Bangkok, Thailand, for their association in organizing this conference. For our profound gratitude to plenary speakers, Professor Gaurav Manik, Head Department of Polymer and Process Engineering, IIT Roorkee, Dr. Sunny Jafar, Associate Professor of Mechanical Engineering, IIT Mandi, and Dr. Jyotish Kumar P., Director, Sophisticated Testing and Instrument Center, Alliance University, for gracing the occasion. A big thanks to all the session chairs, authors, delegates, research scholars, and other invitees for making the event a notable one. I would like to thank the Registrar Admin, the heads of all the departments, section heads, faculty, staff, student volunteers, press and media for their contribution to make this occasion memorable. Last but not the least, I would like to express my thanks to all the coordinators, committee members, volunteers, maintenance staff, and everyone who directly or indirectly contributed to the organization of this conference. Thank you once again. Thank you all.
Thank you, sir. We'll now break for high tea. I request the audience to be seated till the guests leave. And then please join us for the high tea outside, arranged outside, and reassemble back by 12:30 for the first plenary talk. I request the audience to be seated till the dignitaries leave. The high tea is arranged outside. All of you can join us for high tea and reassemble back by 12:30 for the first plenary talk.
I welcome. I take privilege in inviting our keynote speaker, Dr. Malini S., Assistant to the President for University, King Mongkut University of Technology, North Bangkok, Thailand, on the topic, Unlocking Value, the Lignocellulose Biorefinery Journey from Waste to Wealth. Madam, I request you to take over the dais for the session.
Okay. So, thank you everyone for attending my talk today. It is my pleasure that I have been invited to give a talk today. So, I wish that today after I present my research, maybe some of you, if we have any common interest in the research, we can talk more for the collaboration or not only the research activity, but also I have some other activities that I want to showcase to you, and maybe we can have find some common interest together. Okay. So the topic that my talk today will be unlocking values, the lignocellulose biorefinery journeys from waste to wealth. So let me introduce my working place briefly. Oh, okay. This is to echo? No. Oh, okay, great. So let me introduce my okay, great. Okay, so let me introduce about my working place, King Mongkut University of Technology, North Bangkok, or KMUTNB. We established in 1960. Actually, it's a similar age to RIT. I have to congratulate to your university and our university too. So we have 3 campuses. From Bangkok to Prachinburi and Rayong. If we take a look in the map, our 3 campuses are located in the central of the Thailand. So what we have now, we have about 20,000 students from bachelor, master, and PhD. We have about 16 faculty, but mostly we focus more on the engineering, technologies, and science. We do have the ranking result from World University Ranking Institute, especially THE. Thank you. Recently, okay, we got the rank 12,000. However, when we are ranking in Thai University, we are number 2 in research qualities of the THE World Ranking. So right now in our university, we have 2 international schools. First one is business and management, and second one is engineering program, which is my faculty. Okay, so my faculty, we are the international engineering program. So I briefly talk about my faculty. We have motto to do the industry-oriented education. So our faculty have been established in together with the Icamst University in Germany. Right now we have 5 programs from electrical engineering, chemical and process engineering, my program, mechanical engineering, material and production engineering, and railway vehicle engineering. So we have offer for the master and PhD program only, no undergrad student. However, what we have right now, we also have undergrad student who come to working with our faculty as an internship and doing the thesis together for international students. So this is a partner of our university. The left-hand side is the industry partner. We have the Thai partner and international partner like from Germany because our university is also co-established with the German government. We also have the academic partner from different countries around the world. especially in Germany and Europe. Okay, so as I mentioned, what we have offer activity for the international students. I would say like we have communication in English. So I say this is not a barrier for international students. So we have double degree for engineering program, master and PhD with the German university and also UK and Taiwan and Japan. We have the exchange student, so this means the student in RIT or even our university can go to have the exchange intern or thesis work together. So I think we try to extend this activity more because it can be win-win situation for KNU TMB and our partner university. We also have various type of the scholarship. One of them is the DAD scholarship that's supported by Germany government that students can be attend our program in master degree 1 year in KNU TMB and 1 more year full time in Icamst. Okay, so that is all for my working place. Now I move back to introduce myself. So this is my brief profile that I want to showcase to you here. That I am function as a lecturer in my university, and of course I also do have a research project in with the industry and also the government project. Okay, so I have published the paper, more than 160 paper in the Scopus Index database already. I do have the book project, book and book chapter, and also I have the grad student, master and PhD, more than 80 students already, and I have the funding research from industry and government, more than $3.5 million. So I am working mainly in biorefinery, but in next slide I can show you what other research topic that I'm also working. Myself, now I am top 6 author in Scopus, especially in the field biorefinery for the world. In the Scopus 2023, I am ranked number 1 in Thailand in biorefinery. And if you can see my profile, you can see that I have many of international collaboration, more than 50%. So I happy to be here today to looking for more collaboration to international collaborator. Okay, so this is about me. Another job that I'm so into it right now is to be editor. So now I am editor for 11 journal, and some of them are indexed in the Web of Science Scopus. So today I also like to show you here this journal Applied Science Engineering Progress. Now it is in Scopus Q2. The editor-in-chief is my president, Professor Suchasinh Shin. So we are multidisciplinary journal who publish in the science, technology, and engineering. So if any one of you want to submit to our journal, or if you want to join us in the editor team, maybe you can talk with me later about the detail. Okay. So this is my research partner. I have the industrial partner who fund me financial for my research, and also academic partner for different countries right now. I also have many partners from India right now. Like I have Sasa Delima University, IIT Hyderabad, IIT another, sorry, I cannot remember, and also Mahindra University, yes. And I wish that today I may have another collaborator from IIT too. Okay, so this slide, I show you that what are all activities that I'm doing in my lab. I would say this whole project I'm not doing by myself alone. I have a friend and partner who doing different topic of research. So I try to categorize my research project to four main topics. The first one is lignocellulose biorefinery. that I will be my main focus for my talk today. And the second theme is the animal and plant disease detection and management. So we have partnered with my network to do the kit to detect the animal disease and plant disease in Thailand. We have R&D project to develop food and cosmetic product for industry, and also we have, I say, miscellaneous project from omics study like proteomics or genomics project for agricultural application, wastewater treatment, and also biocomposite. Okay. But today, as I mentioned to you, that I will focus on the lignocellulose biorefinery. Okay, so maybe some of you not really familiar with the biorefinery. I would say that biorefinery can be simple to say that it is parallel term to the petrochemical refinery. So the idea, we starting from biomass. Okay, so we have a different process to convert biomass to various types of the products, and then we can convert it to even more applications of the product from various industries. So biomass can be several kinds of biomass, ranging from the food waste or lignocellulose biomass or even municipal waste. So the focus of my research will be mainly on lignocellulose biomass. Okay, so let me tell you about the general composition of the lignocellulose biomass. And I believe that some of you in this room also working with the lignocellulose biomass. It is a very most abundant material in our world. And as you know, I think India and Thailand, we have the same situation that we are agricultural countries. And also we moving toward to the industry country too, right? However, we in every harvesting season we produce a lot of lignocellulose waste, and in my country we just combust it on a site. And what happened? We generate a lot of pollution, especially air pollution like PM 2.5, PM 10, which can be threaten the our health and the younger generation. So we try to find the value from the lignocellulose, but before we doing that, we have to understand what is the composition of the lignocellulose. So basically, lignocellulose can be found in every plant cells. So that's why we can collect it from various types of plants, even they are different in the property, but at the end, the core composition is the same. And those core composition is the cellulose, semicellulose, and lignin. Okay, so from the structures of the cellulose and lignocellulose is made of the sugar polymers, like cellulose is made from glucose and hemicellulose is made from pentose and hexose, and for the lignin is made of the aromatic group of the alcohol. So if we can break down the lignocellulose biomass, we can get the building block that we later can convert it to different types of the product. So the concept of biorefinery, let's say if we were starting from the sugarcane waste, we can extract the waste to different types of the product by using the biorefinery. So as you can see, if we're talking about simple grouping from the biopolymers, biochemicals, biofuels, and bioenergies, to make it feasible in engineering aspect, we have to concern two major property. The first one is the values of the products, the price, I would say like that. Or the second one is the production volume. Okay, so if you can see at the top group, like biopolymers, we can see for 1 unit of scale production, the biopolymer can has high value. However, the production scale of biopolymers is relatively less to bioenergy, like biofuel, bioethanol. So if we compare the price of the bioethanol per unit compared to biopolymer, we know that this is much cheaper, but we can produce it in a much larger scale. So this means if we are engineer, we have to think about what kind of product will be our target for the process. However, one of the important question is that how can we transfer our knowledge to the industry? One of the threatening situation is that the biorefinery, especially biofuels, the price is competitive to the petrol fuel. Okay, so if we observe the world of the price of the crude oil, you can see from spanning of the many years, especially after COVID epidemic season, you see in every country right now we are like facing the price of fluctuated price of the crude oil. So you can see if you are rich and you are a millionaire, you want to invest in oil company. Okay? So if, let's say, if you establish your company in 2009, okay, in 2009, you see that in this year, your benefit will increase like almost 200%. So from $1 million, maybe you go like $200 million. But however, just next 2 years, your benefit down 250% increase. And you can see this is just 10 years period. But the situation is how can you run your business with this fluctuation? So this is one of threatening problem. So shall we move to other point, like if we want to do investment in biofuel, let's say ethanol. If we compare the price of the ethanol yellow color here and the gasoline is the petrol oil, right? So you can see the fluctuation of the petroleum oil is much more than the biofuel. The price of biofuel is more stable. So, however, if we talk about what kind of the raw material that we can use for making biofuel, we can select it from several types. I guess in India, one of the major lignocellulose biomass way that you can have is the sugarcane, maybe like to my country. But if we break down the cost of production and how much of each biomass can convert it to bioethanol, the benefit, the profit from each biomass are different. So this means it doesn't mean that, okay, I have a lot of sugarcane bagasse, but I say this will be profitable for my company. I say really no. So we have to use our research to find and optimize to select our process to be feasible. What about not talking about boring story of bioethanol, but we are looking for the new trend of the bioenergy or sustainable energy, especially for the solar cell. Okay, so I not really have much information for India, but in my country, solar energy is one of uprising trend in Thailand for renewable energy. But again, the question comes back. If you are the owner of company who established your company in 2010 and now just 2024, the price of selling is down 90%. The point is, if you imagine like bioethanol in Thailand, the production price in my country now is about $1 per liter. $1 per liter. The point, if the same question was asked, after 10 years from now, I have to reduce the production price from $1 to $0.1 in 10-year period. How can I do that? For myself right now, I say within 10 years, I cannot reduce my production price down 90%. But the point is, researchers in solar field, I say they are doing so excellent that they can reduce the cost like 90%. However, for the business, how can you do this? In maybe next 10 years, the price reduce 10 times more. how can you develop your project, develop your technologies and the process to reduce the cost more 10 times. So that is so threatening story for researcher and engineer like us. So right now, that's why for myself and the industry in Thailand, especially petrochemicals and agricultural waste processing in Thailand, we try to move away from not only energy or simple story like to manage the waste. We try to look for some other biorefinery product that have more values, not only for the bioethanol. So as I mentioned, bioethanol price in my country is $1 per liter. However, let me tell you here because it's my bad that I'm not convert to the dollar. But baht Thai is 1 baht Thai is about 2 rupee India. So you can see any alcohol which I actually can co-produce with bioethanol, we can increase the price up to 2,000 baht per liter. So the price of other compounds, for example, like linoleol, this one can increase up to 8,000 Thai baht per liter. So this one is, the application is for food additive to increase the aroma for industry. Okay, so you can see now, comparing to the price of the ethanol, this kind of value-added product can increase the price from 30 to 600 times. So this means it's come back to the question that shall we go with the product that we can produce in large scale with minimal price, or we try to look for other products that we can produce in maybe smaller scale but higher value added. Okay, so I would say right now my research lab also working on some of these food additives. So if any of the professors who working on the fermentation and biorefinery, you can talk together if we can find collaboration activity. Okay, so I briefly talk about the process of lignocellulose biorefinery. As mentioned, we have cellulose, hemicellulose, and lignin, and these component actually it is so difficult to be break down. So that's why it's really necessary to have the different process like pre-treatment to loosen the structure of lignocellulose to be more vulnerable for enzymatic hydrolysis, to break down the polymer of cellulose and hemicellulose to the smaller molecules like sugar or oligomers. And then once we have the small molecules, and then we can ferment it to convert it to various type of value-added product. For some of you that are not working in the fermentation, I would say we can create several of bioproducts by using various type of microorganisms, or even use the modified genetic material of the microorganism or GMO to activate the fermentation to produce various type of product. Okay, so I will go to more detail of the pre-treatment. So what is the function of pre-treatment? Pre-treatment is the process that after pre-treatment, let's say this is untreated lignocellulose biomass and pre-treat lignocellulose biomass with solvent called DES or deuteric solvent. So you can see from the structure of lignocellulose is more loosened, and this can increase the surface contact area to the enzymatic hydrolysis, and also has some other function like remove inhibitors and make the water accessibility for the enzymatic hydrolysis. So the good pre-treatment should be low cost. Of course, we are engineer, we have to go with low cost, minimal energy consumption, and maximize sugar yield, minimize the toxic compound or inhibitor, and should be environmental friendly. However, the point this cruel world is low cost and environmental friendly, they are mostly not sit together. So we have to compromise this and looking for the technologies that can make us toward the green world. Okay, so let me tell you, I actually working in the biorefinery for like 10 years already. In the early years, I using the chemicals named ionic liquid, and I believe that some of you here working for the composite, you also use ionic liquid to be the solvent for solubilize your cellulose compound for fabrication. So ionic liquid is the compound that we consider is as a salt because it made from cation and anion similar to sodium chloride. However, the property of ionic liquid, as I say, is like liquid. So this means at the room temperature, it has the liquid property. So that's why it's suitable for pretreatment application. So it is a green solvent. The property is related to environmental friendly process like low vapor, thermal stability, chemical stability, non-flammable, and okay. However, one of the disadvantages is that the price of ionic liquid is very expensive. For the lab grade, I say the price of one of very effective ionic liquid that can solubilize cellulose very well is the ionic liquid named imine acetate. Okay. However, the price of imine acetate is almost $18,000 per kilogram. So how can this work in the industry? Definitely, if you produce bioethanol, say no. Okay. So it seems to be very good one for publication if you are a researcher who looking for excellent process that can recover, say, 99% of cellulose. Of course, ionic liquid is a good one. However, maybe it's not really practical for industry application. Okay, so let's see. This is the flowchart process for ionic liquid pretreatment. So if you can see, if you take this process flow to the industry like this, maybe they don't like, because you can see so many of the reactors and the process, especially the separation process. This can increase the energy cost and operation cost of the process. So quite complicated process. So that's why now, about 7 or 8 years already, the researcher or engineer who working with the pretreatment try to working on shift from ionic liquid to DES, or the name is deep eutectic solvent. The idea of deep eutectic solvent is so similar to ionic liquid that ionic liquid has cation and anion, right? But for DES, it has hydrogen hydrogen donor atom and hydrogen acceptor atom. So it's more like cation and ionic. So in the case when we have DES solvent, we also have the liquid form mostly at the room temperature. So that's why it is suitable for the pretreatment application. The interesting thing is DES is also green. It is recyclable and environmental friendly. Story is even more interesting that the chlorine chloride, that is the major composition for DES, the price down from ionic liquid $18,000 to $100 per kilogram. This is lab grade, I say. But if we talking about industrial grade, in my country, chlorine chloride only $2 per kilogram. From 18,000 to $2 per kilogram. So this is more potential compared to ionic liquid. However, it's not okay. I found the cheaper and I go with DES. Actually, it is not really like that, because if any of you in this room working on ionic liquid or DS, you know that it has some selectivity, like ionic liquid prefer more on the cellulose. However, for DS, it's more preferable to lignin. Okay, so this means if we have different selectivity, we will have different design for the process. Okay, this is the slide to show how DS can solubilize the lignin and extract lignin from lignocellulose biomass for further processing. Okay. Next one. I actually, this is not really, I don't want to talk much about it, but because today is my turn and I'm looking for collaboration, I just want to show you here that in my lab, we also working on the development of enzymatic hydrolysis to develop a cocktail of lignocellulase enzyme for industry application. So what we have being in my lab right now, we have the develop the microbial consortium and using the genomic technologies to see the progress of the equilibrium of the microorganism member and extract the enzyme and test for the activity. Okay. If you use too harsh condition of the pre-treatment, for example, let's say if we pre-treat lignocellulose biomass, cellulose can be break down to glucose or galactose, and then this can be converted to HMF. This one is the inhibitor for enzymatic hydrolysis or inhibitor to the cellulase. And also, if the concentration is too high, it can kill yeast that we use for the fermentation process. As well as the furfural, which is actually inhibitor in our process. However, if we're talking about industry, producing HNF or furfural, this is not the really inhibitor, but we can process, separate it, purify it for selling as a value-added product in the industry. Okay, so however, in my process that I proceeded to fermentation, I want to minimize formation of HMF and furfural. Okay, so this is another area that I'm working in my lab, that we are developing the process of fermentation that compatible to the pre-treatment process. For example, if we have ionic liquid, ODS or other chemicals that is the toxic to yeast fermentation, we have to develop the fermentation process to compromise the inhibitory effect to the fermentation. For what I'm doing right now, I develop the process for HF and SFF to compatible to my pre-treatment process. So what is the SSF and SSF process? Briefly, I say SSF, we will do hydrolysis and fermentation in different reactor, different timeline. Okay, so this you can think like we have at least 2 reactors for the process. However, for the SSF, we will do the hydrolysis and fermentation in 1 reactor and at the same time or different timeline. So this means if you have 2 reactors here, 1 reactor there, if you are the owner of the company, you have to invest for the big reactor. This can cut the price of investment cost by half already. All right, so I move to the topic of my research, that if you can see the general process for produce the ethanol from lignocellulose, you can see we have to cut it 1 reactor, no? And then we have pre-treatment process, 2nd reactor, enzymatic hydrolysis, the 3rd one, fermentation, the 4th one, and we have the recovery, the 6th one. So you can see there are 5 or 6 reactors, not including the separation process. This is the investor, the owner company have to pay money for. Okay, so, and this is not including the manpower to control all these reactor. Okay, so now what about we try to consolidate the process by combining different steps into one reactor or even one time reaction. Okay, so we can do many designs from combining pretreatment hydrolysis together, or we can combine all the process together in one reactor in one reaction. Okay, so now I have few case study to show you what we are doing in my lab. Firstly, as I mentioned, I working with ionic liquid. You can see for untreated cellulose biomass, when we solubilize this one in ionic liquid, amine acetate, we can see it's completely solubilized cellulose very well. And after that, what we do is we take the cellulose to hydrolyze to get the resin sugar. Okay, so you can see comparing to untreated here, the amount of releasing sugar just this much, but when we pre-treat it, the sugar concentration is almost 90%. So this is very effective chemical for pre-treatment. However, the problem is when we have ionic liquid residue in pre-treatment and we want to get rid of it by washing. However, if we don't wash it very well and still have ionic liquid remaining in the enzymatic hydrolysis reaction, comparing to the one that does not have ionic liquid, the enzyme is 100%. However, if we have just 10% of ionic liquid, the activity reduced almost 60%. So this means you need extensive, okay, thank you. You need extensive washing to clear this ionic liquid. And I would say how much water. I frankly tell you that in my lab, if we want to wash ionic liquid from biomass, 5 grams of biomass, we need 3 liters of water. Gram of biomass, this much, we need 5 liters of water to wash it. So how come that we can transfer this to industry? You generate huge amount of wastewater. Okay, but I can publish many papers from this because in lab scale we claim that, oh, can we get the very high sugar, very effective? We can publish many papers. But in my another corner of my heart, I say, oh, this is not applicable. Okay. So then my strategy, what to do is we try to develop the process to be consolidated from the conventional one that we have, pre-treatment of ionic liquid, and we have extensive washing, and then we can do enzymatic hydrolysis, okay, this one. And one of my published work is one-pot process that I minimize, actually remove washing step. Take it out because it's burden in my heart. I want to take it out. So what I did is I make it to be one-pot process without washing. However, as I mentioned in the previous slide, that ionic liquid is inhibitor to cellulase anyway. What we can do, we can develop the ionic liquid tolerant cellulase enzyme to be used in this process, and then my problem is solved. So this is the ionic liquid story. So the detail of that work is our lab, we also do microbiology research to screen and identify and extract the ionic liquid tolerant cellulase enzyme, and we characterize and study the kinetic of our cellulase. So comparing to ionic liquid, this one choline acetate, which is the low toxic ionic liquid to cellulase enzyme. In my lab, we screen for the ionic liquid that is also low toxic to cellulase enzyme, comparing to very efficient chemical but high toxic to cellulase enzyme. You can see that when we add the concentration of ionic liquid, the reduction of enzyme activity here for low toxic one is smaller than comparing to the high toxic ionic liquid one. Okay, so we can design our process to make the feasible, practical process by using ionic liquid. Okay, so this is, I would just give it because, but briefly, I want to show you that in our lab, we also do kinetic study to see and analyze the function of inhibitory effect of cellulase enzyme, of ionic liquid on cellulase, how much we can compromise or minimize the inhibitory effect of cellulase or to our process. Okay. Next one, deep eutectic solvents. Now, I would say my member in the lab, we now moving on to the DES. I would say, frankly speaking, from my own experience, I say ionic liquid is more efficient comparing to DES. However, still, even I can publish many papers from ionic liquid, but inside my mind, I still cannot overcome the problem in my mind that ionic liquid is 18,000 per kilogram, $18,000 per kilogram. This is impossible for industry. So that's why I try to move away from ionic liquid to much cheaper chemical like DS. Okay, so DS can also working well for lignocellulose fractionation, and my collaborative partner in KMU TNB, we also separate the fraction of cellulose, hemicellulose, and lignin, and we separately sell lignin as an ingredient to the refinery industry in Japan. So lignin separate from this process by DS can also be sold as a composition, because at the end the company who sell who buy our lignin can use it as a ingredient for biocomposite for making other final product. Okay, so what I want to show you briefly here is that DS will form very low content of inhibitory like HFF and the furfural, and it can also very working well for increasing the efficiency of enzymatic saccharification or hydrolysis. So you can see, comparing to untreated biomass, the sugar yield can increase 60%. Okay. So the similar knowledge that we are using for ionic liquid, we also develop and apply it to DES. So what we are doing here, we have, let's see, my eye is long side. Okay, we have different of DS, which is the chlorine chloride, lactic acid. Okay, so we can see that the cellulose glucose composition can be increased by after pretreatment. Okay, and then when we want to do one pot process, we have to assess whether the DS has the inhibitory effect on cellulase or inhibitory effect on yeast. So we do test both. Let's say for the cellulase enzyme, okay. So if we increase the concentration of DS from 0 here, the blue bar, to 15%, the gray one, the activity almost down to 0. But the compromised one is 10%. In another case, when we test the inhibitory effect or toxicity of DS on yeast, we found it has no effect on the yeast growth. So at the end, we can say that, okay, no toxic to yeast fermentation, but toxic to cellulase enzyme. Okay, so we cannot just mix them all together in one pot without any design. What we do is we still develop the one pot process comparing to HSF, the separate process. So as you can see, in our one pot, we can have higher final product comparing to SSF. But our tip for this process design is we are not directly just mix our DS into the fermenter or to the hydrolysis reactor. We have to reduce the concentration of DS down to 10% first, and then we put together in one pot. So at the end, we can reduce 2 reactor to 1 reactor. So this is more applicable for the concept for the industry. Okay, so I keep talking about sugar and ethanol. So during our process, as I show you in the slides of the aroma compound, we not only produce ethanol, but we can produce other value-added products like wax. So in this study, we try to produce, co-produce wax and ethanol together because we know ethanol is cheaper. Even we can produce in higher cost, in higher volume. But comparing to wax, that we extract the wax and recover it, and we do the economical analysis to see if this business is possible. And at the end, we found that if we take the revenue of wax recovery, we can make the higher revenue about 1.64 times comparing to the process that produce ethanol only. So this is the concept to plan for our process. How many minutes do I have left? Please, 5 minutes, okay. So here, just to let you know that we also working on several parallel process, try to making it to be one pot process to minimize the investment cost, operational cost. We also try to looking for co-product that can increase the value at the same time. So in this case, we have comparing between unwashed process. Again, as I mentioned, after pre-treatment, we do need to have extensive washing. So I show you here that if we don't washing the sample, you can see that the production of the product is much reduced. It is showing that this is necessary if we are not design the process to avoid the washing. Okay, I will just skip this. Okay, I think this is almost the final case study in my lab. One of the industry application, especially in my country, I'm not really sure for the other country, but the point is, if any one of industry process is designed originally to strictly to one type of feedstock, for example, like ethanol plant for sugarcane molasses. Definitely, if you're working with industry, they will not take the risk. Just, oh, okay, today sugarcane molasses is expensive, I switch to starch. Industry cannot do that because the process is not compatible. But the point is, for biorefinery, if we say our process designed for sugarcane bagasse, and if someday, and you know global warming, it has been estimated in 20 years from now on, with this global warming rate, sugarcane will be extinct, like the same time with the cocoa and coffee. In just 20 years, global warming will make it extinct. But in that time, at that time, we don't have sugarcane bagasse, then what we can do? We have factory already, but we don't have feed, input feed. So my question come like that, and then I come the reason, the problem is that I want to investigate whether I can mix many types of lignocellulose if someday sugarcane bagasse is extinct. Can I use nape grass? Can I use rice stalk, or can I use some other plants in engineering as perspective. So what we do mixing several formula of mixed biomass, and then we process the same process like we do in single type of biomass for production of ethanol. And at the end, we can finalize and see that the sensitivity variation of the mixed biomass is only 4% and 8%. So this is the evidence that we can show and convince industry that for now you don't have to really depend on one type of biomass, but you can use mixed biomass. However, you need to do research and study to see how can you formulate it. It's not just simple like mixing whatever biomass together without any principle and you get the same result. No, we have to do research and plan for formulation and test it and make sure that the variation is only 4 or 5%. Now, I can say, okay, with this model, we can do mixed biomass for our existing process. Okay. All right. In my lab, we also do produce some other higher value like silo oligosaccharide. This can take it from hydrolysis of hemicellulose. So what we do, we are using different technologies like microwave or chemicals to produce, and we have different profile of XOS. And some of you, if familiar with the XOS, we can use XOS as the probiotic product. We can do some simulation, intestinal digestive tract simulation for our experiment and see how the XOS had effect and if it's suitable for being the food supplement for human food or animal feed. Okay. And the last project that I want to show you here today is one of ongoing process that we just get funding for is using the production of plant protein by using the green chemical solvent as the extraction. Okay, so what we are doing, this is not my publication yet because we are doing on it, but the concept I want to show you here is in Thailand we has the consumption various type of protein from animal and plants. However, now we try to move forward to the greener society to consume the plant biomass like plant protein for alternative food choice for the people. So that's why now we are developing the DS solvent to extract protein, and after that, after we extract the protein from lignocellulose biomass, we reuse DS to fractionate lignocellulose residue for ethanol production. So this is gonna be close the gap of circular process to meet with the circular economy concept. Okay, and we analyze the property of the protein if it's suitable for food supplement. Okay, so that's it. The case study, the activity ongoing for my research that I want to show to you here today. Thank you for everyone, and I would thank my student and post hard in my lab. And also I want to show you that I have many of the international students who doing research in my lab right now, short term and long term. I'm open for that, and we have some scholarship and financial support for the student too. Okay, thank you everyone, and if you have any question or comment, or like if any professor want to discuss with me after talk, please come stop by to talk with me. Thank you.
Any questions?
Yes, Professor.
First of all, I would like to thank you for giving an excellent talk in which the true research outputs is usable to the industry. It was very heartening to see. translating your lab research and taking it to the land. Can you just give a brief account of that?
Sure. Okay. I would say in my research, as I show you in the slide, that I have 4 categories. I have, let's say, from the simple thing like food and cosmetic industry first. I would say food and cosmetic industry, I would say investment cost. If like researcher like us develop new process, and then we translate this pilot process product to investor. Okay, this they have they use small amount of investment. Like I say, one of our product is the congee ready to eat. Congee ready to eat. We sell to the investor, and now the product is sold in Germany. The owner spend money like only 10 million Thai baht. 10 million Thai baht to develop this process to be sellable product. But talking about another project that I working with sugarcane processing factory, they have the problem to fermentation because the yield of conversion between molasses to ethanol is drop significantly because the weather is too hot in Thailand and yeast die in the tank. And then I developed the process by using some magic material, and then I suggest them, I test them because I got a financial support from them. I test it and I have like economical analysis to show them like if you use my magic composition, this one, you can save the loss of ethanol 1 million Thai baht per day. 1 million Thai baht per day. Some of you may think, if I the investor, I will pay money to buy magic component from me. But frankly speaking, at the end, this project, the company don't continue to this project because they say the scalability of the ethanol processing plant, if they have to purchase this magic material from me, they have to spend money almost 100 million Thai baht. So if I am CEO and then I have to spend money 100 million Thai baht with not high credential researcher like me in their eye, they have some reluctant mind comparing to cosmetic product 10 million Thai baht. So this is, I say, sometime and many projects that I show good result in research to the company industry. They say, okay, this is very good result, excellent. But at the end, they don't continue to invest. Yeah. Yeah. Sure. Thank you, Professor.
Thank you, madam, for sharing your expertise with us.
Thank you.
Now we will break for lunch and reassemble back here at 2 p.m. for the plenary sessions.
Thank you.
Very nice.
Good afternoon, one and all. I welcome you all for the plenary session. I take privilege in introducing the plenary speaker for the day, Dr. Gaurav Manik. He is professor and head of the Department of Polymer and Process Engineering, IIT Roorkee. So Dr. Gaurav Manik is holding this position since 2013. So he holds a PhD from IIT Bombay, MTech from IIT Kanpur and BTech at HBTI Kanpur in chemical engineering. Prior to joining IIT Roorkee, he has served extensively in industry and academia, and totaling his experience up to 20 plus years. He is credited with creating and commercializing several innovative products and fostering IP through significant number of patents and record of inventions. His research interests include applied molecular modeling and simulations, sustainable hybrid polymer composites, and environmentally benign nanocomposites, bio-based adhesives, easy clean coatings, valorization of waste, carbon sequestration, etc. He has got around 200 research publications and 91 publications in peer-reviewed journals and 10 granted patents and 26 book chapters. And he has guided around 2 postdoctoral students, 8 PhDs, 16 MTechs and 25 BTech students. He has got various awards into his credit, Best Innovative Product Design Award twice in 2010 and 2011 from 3M, and secondment as visiting faculty sanctioned by the President of India for teaching at International Platform of Asian Institute of Technology, Thailand in 2016, visiting faculty at Khalifa University, UAE, and various other universities. He is the fellow of Institute of Engineers and Indian Institute of Chemical Engineers, and is an invited speaker, guest and session chair at several national and international conferences and workshops, and he serves as Board of Director of STEM Research Society India. Sir, we are honored to have you with us today, sir. I request Dr. Nagaraju Kottam sir to invite him with the bouquet. Now I request Professor Manik sir to take over the dais for the session.
Thank you for a wonderful description about me. Good afternoon. So I'm going to speak upon this topic today, which is sustainable and performance polymer composites for emerging industrial applications. I come from IIT Roorkee, and my department works in the area of polymer science, polymer engineering, and also in the area of industrial process engineering. What I'm going to speak to you is today is several research stories which my students have worked at, either solely academically or in collaboration with industries. So I'm going to talk about several stories, and then I'm going to focus on one such story. Okay. So before I start, acknowledgements to several of my students, acknowledgements to organizers of Icamst, and all the faculty who have given such a kind, hospitality to me. So really appreciate, several faculties who are working day in and day out and welcomed me so nicely. So thank you for that. And these are my students, some of whose research I'm going to present today. I'm hopeful that you will find it quite enlightening, and something new will be a takeaway from today's talk. So just quickly, what my group does these days. So what advanced hybrid composites. So what we understand from this is, when we talk about automotive, when we talk about four-wheelers, or let's say when we talk about aerospace, the most interesting thing or the most point of interest is how to make these vehicles, four-wheelers, or let's say aerospace lighter, because there is obviously a concern of mileage which is attached to it. You would like, from the your pocket viewpoint, you would like your cost to be as low as possible, your four-wheeler to burn as less fuel as possible, or let's say in terms of aerospace, the less amount of CO2 which goes into the atmosphere. So you would like least amount of environmental concerns because of pollutants, so you would like to enhance your mileage. And one of the ways which you can do this is quickly is if you can reduce the weight of your four-wheelers, two-wheelers, or aerospace. as per the data, it says that if you can reduce the weight of your four-wheeler or two-wheeler or aerospace by 10%, that will lead to a reduction of about 7% in your, pollutants which you go out, or it will enhance your mileage. So if you can reduce the weight by 10%, you will reduce the consumption of your fuel by straight 7%. So there's a very good correlation, and that motivates all the two-wheelers, four-wheelers, and the aerospace industries to reduce their weight. That's all what we've been doing in the area of advanced hybrid composites. I'll just take you a little later around the story, what we've done. But that is one area of interest. The other area of interest is molecular modeling and simulation. We've done a lot of work in this area, and people normally look at theoretical pieces of work at a distance, but what we've tried to do is to couple these molecular simulations to understand the properties of polymers, polymer composites, and polymer nanocomposites in detail. So it's not a tool only which characterizes your system, but it is also a tool which helps you screen your system, because it may give you a guiding light of what would be an optimal formulation without actually synthesizing, your chemicals or the polymers or the composites. So I'll take you a little bit through this also, wherein, it is not only a characterization tool which tells you about the structure property relationships of polymers and polymer composites, but it also tells you what actually to synthesize and what not to synthesize. This helps you reduce a lot of efforts and, synthesis efforts, and also saves a lot of your resources. So I'll take you something around this molecular simulations. I'm sure many of you would not know about it, but would find it interesting. The other area which we also work is self-clean and easy clean coatings, where, we are aware of the lotus leaf effect, and we try to make nature-inspired coatings. Prime interest is to make them easy clean, and one of the ways to do it is if you can make the surfaces super hydrophobic. When I say super hydrophobic, which is more like a lotus-like, it is like having a contact angle of 160, 170, 170 degrees plus. And this is possible through a selective choice of the additives and a selective choice of how you tune your surface. Okay, so I'll take you briefly around this also today. And the whole interest is, how you can use sustainable materials to develop those coatings and also yet not compromise upon the performance, which is the superhydrophobicity, or which translates into the self-cleaning of your surface. Many of the ladies here would have seen, you have exhaust fans in your kitchens, and you know that normally an exhaust fan is brought down from its place only when it is about to be thrown off. It's spent several years of life, 10, 15, 20 years, that exhaust fan is never to be cleaned. It never gets to be cleaned because it is so greasy and so, badly managed. You don't feel like taking it out and cleaning it. And that's one of the areas where, you can make a change. How you can treat those exhaust fan blades earlier before it is installed, and, you don't have to clean it at least for some more years. Okay, so that is some of the examples, but there could be pretty other examples in our everyday life. The other area that we also work is process modeling and simulation. In industry, there are several energy-intensive processes, and one of the energy-intensive processes which I would like to mention over here, we've got several chemical engineers and mechanical engineers also over here. One of the things that we have, which I show over here, is your multiple effect evaporator. To talk about crudely, a multiple effect evaporator is something which actually evaporates a lot of your solvent. For example, in a fruit juice concentration, you will have to evaporate a lot of water so that it thickens. It could be a sugar cane juice. It could be, in one of the processes like a paper mill, where you have a lot of black liquor, a lot of solids, you try to concentrate. So when you try to concentrate, you have to evaporate a lot of water, and which is very energy intensive. And there could be several other processes. So what we essentially do is try to tame some of these processes, make them more sustainable by integrating them with, processes like, sourcing from solar energy. So there is something called, which I show over here, is a parabolic truss solar concentrator, which we integrate with these natural, with these intensive processes, energy intensive processes, and make them more energy efficient. So this is, one way how you can bring in more sustainability. So this is one area where we, model the systems and, propose the optimal process parameters. The other interesting, and in fact it is one of very interesting areas which very much matches with the theme of this conference. This is around sustainability. Upcycling of waste. Today we not only talk about recycling, but we also talk about upcycling. Upcycling is that, can you add value more? So if it is a waste which is costing like 10 rupees, can you, use it in a way such that you can improve its value to about 100 rupees or 1000 rupees or more? So one of few of the examples what we've been doing is the fly ash which you get from industries, primarily thermal power plants. It's absolute waste, and companies like NTPC, if you ask for fly ash, they may send a truck down to your doorstep if you can use it. They are so much troubled for disposing it. You don't have to call someone, some industry, can you, share me the price of it? They'll say, we'll send you the truck along with the fly ash, free of cost. That is the whole trouble of disposal of some of these waste. And how you can utilize them in making products, which is, useful for the society. So this is some area which we also work at. I'll talk briefly if possible. Then we also work in this area of green adhesives. And adhesives, we all know, when we talk about adhesives, something which comes to our mind is the Fevicol, right? Everyone knows Fevicol. Everyone knows sellotapes, the tapes we use in stationery purposes or the other purposes. These are all adhesives. There is a growing trend, can you make these more sustainable? Why? Because you see an apple over here, you many times get these apples with those stickers on top, and you sometimes fear that you have these synthetic, adhesives which might be attached to it. So you ensure that once you take the sticker off, you wash it 3, 4, 5 times. So the interest is, can you make these sourced from biomaterials? So that is what we have done some work. Plus, you might have been, I hope you never get to go to hospitals, but sometime or the other we get to, and we have these, tapes or the bandages applied to our, bodies. And if these lie there for a few months, or I would say a few months, if it is like a week or 10 days, and then you take it off, then you get those, dermal issues. Your body gets red at that specific location, remains there for such a long time. You would not like that to happen. And so the issues of dermatosis or, those dermal reddishness that you observe, that also happens because you are using chemicals and not biosourced ones. So what we have delved into this area is, can we have biosourced materials which also perform equally or even better than those adhesives which are sourced from chemicals? Okay, so this is one area which I am going to quickly talk about. And this is one such material which we use, which is the linseed oil, and it is a non-edible oil. So you don't disturb the food chain, and yet you make very good high-performance adhesives. I'm going to talk about some of these things. In terms of what my group has achieved out of this, several publications and, in peer-reviewed publications, hot access articles, some of these hot access articles and, research reports in media, and several conferences, patents, books, PhDs. These are some of my accomplishments. But more importantly, industry has shown a lot of interest, and we've got very good funding from these sponsors: Indian Oil, Denier, Casper, Center for High Technology, IOCL. So a lot of these industries have funded us, and thank you. While I speak, while I talk about all these products, it's my duty to thank them over here. So I appreciate all those sponsors, and some of these works that I'm going to show you is the Industry Connect work. Okay. Now let me go forward quickly. Is the first thing which I was about to talk about, the first area, which is the advanced hybrid composites. Like I said, you would like your vehicle to be light. You would like your four-wheeler to be light, so light that you see over at the top, the four-wheeler, the car that I see. The thought is that if you at some point of time in life actually your car gets broken, when I say broken, it breaks down. you and your wife are there or you and your friend are there, this should be so light enough that you can actually take it and move it at least to a few meters, nearby. So that is the whole concept, how we can move in that direction. And there's a strong interest of some companies who are actually very seriously moving in that direction. And how is it possible is how you can make these from materials which are not only lighter but stronger as well. So what we are targeting over here is the strength per unit weight. Okay, so this is a different property which is called as a specific strength per unit weight. So that's what we are targeting. So you would need to use materials which enforce or reinforce, if I have to specify, reinforce the polymers, and they also are lighter in weight. Okay, so this is the story which we started upon, and this is the challenge. The second is, these additives, there is a low compatibility of these additives with the base polymers. When I talk about engineering polymers, which is polyethylene, polypropylene, and similar ones, these some of these are very non-polar. These are organic source, so they are non-polar. And when you add additives like fibers, let's say sisal fiber, hemp fiber, or any kind of fiber, cellulosic base, these are relatively, so you have a less polar one meeting a completely non-polar one, so it will not merge or it will not disperse very well. And when a fiber or an additive does not disperse into a base polymer very well, then it will not reinforce it. Okay, so the whole challenge is how to make your additive polar, okay, and your matrix, you can't make it polar obviously, so you will have to have a compatibilizer in between them. Okay, so the concern is to increase the compatibility between the additives, which is the fiber sometimes, and the matrix. Okay, so this is an issue we're going to talk about this year. And the other thing is, let's say if you're taking carbon fiber is well known to everyone, right? You use it in your rackets. So the rackets which I show over there, sport articles, these are carbon fibers which go there, very light. If anyone has played badminton at their younger ages, some of oldies like us, you would see these rackets were made of wood, very, very heavy. You play like 15, 20, 30 minutes and you say, I'm done with it. So that point of time, these were like 200 grams, 250 grams, one racket. And you know how much is the weight now? Sorry? No, the GSM is not the weight thing. GSM is grams per square meter. It is of that. Yes, but I'm talking about the racket, the weight of the racket. But very coincidentally, you came very close to the number. The weight is actually, yes, 69 to 70 grams. So we have come down all the way from 250 grams racket, which we could not play much, down to about 70 gram racket, which is so light. You can play, you can smash like anything. So, the whole technology has made our life much easier if we actually feel it that way. So 70 gram racket, and look at the Air Force parts, the aerospace parts, the four-wheeler parts. The first Maruti car that I drove, Maruti 800 used to be there. It used to be very heavy. That small car also used to be very heavy. Even driving and moving the vehicle was, wheel was very difficult. But now these are much lighter. Even the, two-wheelers used to have a lot of screws there, which would make a lot of noise, all the time. A lot of these small and even body parts, big body parts, have now been replaced from metals towards fiber bodies, which is all polymers which have been reinforced with fibers. Okay, and one of the very interesting material is the carbon fiber, because it is much stronger than steel as well when we talk about models. So obviously we can't take and make these parts only with carbon fiber. We take polymers, because carbon fiber itself would be very expensive. We take carbon fiber and we add it to the base polymers. And this carbon fiber actually reinforces and makes it very strong. The whole polymer-based reinforced carbon fiber composite is very strong now. Okay, so this is what we're going to talk about. Now the next level which goes is how to make this composite or the carbon fiber even more stronger to reinforce. Okay, so what people have been doing and what we've also tried to do is you functionalize these carbon fibers onto the surface, okay, such that it is more connected with this surrounding matrix. And when it is more connected, interlocked with surrounding matrix, whatever load you will put on the part, this fiber will be able to take it. So one of the reasons to take fibers into composites, polymer composites, is to reinforce them. And reinforcing will only happen when you have a good interlocking of the fiber with the surrounding matrix. Okay, so this is what. So what you could do is you could use molecular simulations to actually predict what is the right functionalization route. The other is the experimental route to treat carbon fibers. So this treatment could be of several means, but we use electrophoretic deposition. That is one technique, and you can treat these carbon fibers and reinforce them. Okay, now this is quickly some other stories which is around the molecular modeling and simulations to make self-clean coatings. When it comes to doing something using nature-inspired stuff, which is, let's say, lotus leaves. I don't know much about biology, and I don't know much about plant and how the leaves are made up of, but I just know that the structure of a lotus leaf has these microstructures, and then it has what nanostructures in this. So this nature uses a very interesting combination of microstructures and nanostructures together, which gives it super hydrophobic property. I understand those biochemicals which are involved also contribute to it, but your exact combination of meso or the micro and the nanostructures makes it do that. And this is what exactly we try to do. We try to choose some micro level materials like carboxymethyl cellulose, and we made some nanomaterials like zinc oxide quantum dots, and we added them together in a polymer matrix and coated it. And this is what are the results. And so we have these zinc oxide quantum dots which have been coated onto the surface. And as you keep on increasing the level of these quantum dots and the combination with microstructures, your contact angle increases, and you can see the contact angle went from about 90-100 for the polymer matrix to about 150-160 degrees. So what I'm trying to represent from here is we can take inspiration from nature, we can implement things in a similar way. There are several biomaterials which are there, or at least biocompatible materials which are there, or those which you can make and create similar structures. So it is possible to solve problems. People may say, what about performance? What about this performance? What about that performance? But definitely you can make some leaps towards making sustainable, products, something like a sustainable coating like this. Okay, so this is one such example which I wanted to show. And then this is the other interesting example which I was talking about, fly ash based composites. We were trying to imitate the properties which some of these four-wheeler companies are trying to do. Some of the examples which I show over here, if you talk about Dodge, Ford, Mercedes-Benz, Daimler, Chrysler, Audi, so some of these companies have been trying to do it since I would say about 2014-15. Some of these companies actually make these automotive parts using the natural fibers. And these properties which are reported here, we were able to replicate these properties, not even replicate but get better beyond them. And what we've taken a natural mineral fiber, which is the basalt fiber, and the fly ash, which I mentioned as a waste from power plants. And together we could make this, as a very strong composite. This number of 9.31 flexural modulus and a tensile strength of 48 has never been reported. Let me tell you, all the patents we searched at, this has never been reported. This is a classic example where you can valorize your waste, where you can improve the value of your waste, okay, if at least you can make some such products. So this was patented by us, and very interesting application. I won't say completely bio-based, because polypropylene or polyethylene or any other commodity product that you take, polymer that you take, will obviously go into it, but there is a lot of reduction in the amount of chemicals that you use here. The other example in the center is that of nanofly ash with sisal fiber. The first case was a mineral fiber, the other case is a case of a cellulose-based sisal fiber. So similar results, though not very strong as the case with the basalt fiber, but you still look at numbers like 30.84 tensile strength and the flexural modulus of about 1 GPa. This compares well with the work which has been done by the automotive as well. So this, primarily the automotives will look for two important properties. One is which is the tensile strength, and the other one which is flexural modulus. And these results clearly show that you can make several steps. You can take several steps towards making things sustainable, and yet not compromising on your performance. Okay, so that's the possibility. The other one is the impact of treatment. Now, many of these natural fibers, some of you who would be working in the area of cellulose-based fibers, sisal, hemp, wood, or whatsoever, will encounter one problem. A lot of these fibers have the moisture absorption tendency. Okay, so any product that you will make will start to absorb moisture, and after some time, it will start showing its problems. Coincidentally, with this fly ash as an additional additive, it tends to reduce the absorption of the moisture by these natural fibers. So this was like, I would say, silver lining in the cloud that, fly ash added not only gave improvement in properties, but also, reduced the moisture absorption tendency of your product. Okay, so this is another interesting thought. Now, this is around the modeling I was talking about. The energy intensive processes, you can model them. So we've tried to model these multiple effect evaporators. We've tried to model and integrate these with the parabolic trough solar concentrator. I was told by your faculty that there is a parabolic trough concentrator probably on the roof of this building, which I'm here to see. And our IT group is doing very well in terms of utilizing this. I'm hopeful. But on a bigger scale, you can actually couple these solar processes, integrate them, if you can model the system nicely. So this is one piece of work. Okay. Now this is what I was talking about, making the biosourced PSAs. Okay. To replace the chemically synthesized adhesives. When I say PSAs, I'm talking about pressure sensitive adhesives. You remember you put those post-it notes on your tables, you write something and you stick them on your tables, those yellow ones, and what you do is you write something and you put it and you press it a little bit. Okay? If you don't press it, it will not stick. So that's why we call it as pressure sensitive adhesives, because you're applying a pressure and so it is getting sensitive and activated and sticking. So in brief, we call as PSAs. Now the work here, what we did is we took linseed oil. Linseed oil is a non-edible oil, and it has several double bonds. Okay, it has several double bonds, and you can very nicely manipulate these double bonds. You can epoxidize them first, so that's the first process of epoxidation, and later you can either transesterify or you can acrylate. Now the intention of doing this is converting an epoxy to an acrylate group, because an acrylate is much more polar than an epoxy group. So if you can make a material which is polar, it will have relatively more tendency to stick to metals like steel surfaces, or even to any surfaces you want to stick at. So the whole intention was to make this something what we call as acrylated epoxidized linseed oil. And then you polymerize and you cross-link this and you make your final adhesive. So what I wanted to tell from this story is, there are several sources of bio-based material which can be made to source and do a better job than those which are already existing, chemically sourced. Okay, just to tell, the bottom figure that you see, is a simulated skin. Okay, not many people, I would say, hardly any researchers who have tried to simulate skin. So when the problem is you want to see that reddishness on your hands, the first thing which you also want to see whether your so-called bio-sourced PSA will stick well or not. Obviously, it's very difficult to ask my students in the lab to go out, call people, and you try this adhesive on their hands and see what happens and see whether it is sticking well or not. This is not very practical, and there may be several questions in the department, because for clinical trials or even very simple things like this, there could be several concerns. So, a very interesting way to do was through molecular simulations. So we modeled the whole skin, what it is made up of, and we modeled this whole adhesive, what it is made up of. We applied it, and through molecular simulations, we actually pulled it and saw how much strength is needed to pull it apart. Okay, so we can capture that strength in molecular simulations. And we did the same thing using a commercial chemically sourced PSAs. We modeled that and we also pulled it. And what I'm going to present now to you is, these are the results of several commercial PSAs which are there in the market, and our numbers clearly stand out, or at least are close to those numbers, which is 3.58 Newton per inch, which is the peel strength. So I capture the strength needed to pull this from my surface. I call it as peel strength. That's the peeling strength. So this we can also capture both experimentally and from simulations also. Wonderful work by the students in terms of it was meeting several of the properties of PSAs available commercially. Now let me just go to this, the story that I was talking about, which is advanced hybrid composites. Okay, this is one of the very interesting thing, and I said that one of the most important thing is the carbon fiber, and how you can functionalize, how you can coat it, and you make it dispersed well in the polymer, such that it starts taking the load of the polymer. Because obviously a polymer product will be impacted or stretched or whatsoever. But this fiber, which is carbon fiber, which is sitting inside, it is taking the whole load of the polymer, because it is very nicely interlocked with the surrounding polymer matrix. Okay. Now, what to do on this? So we try to attack this problem from both simulations perspective and from both experimental perspective. And from the simulation perspective, I will take you through the experimental results also, very interesting results. But let me take you through this journey of molecular simulations, how we could solve this problem. And I'm sure many of you who have not heard of molecular simulation will start loving it and would like to implement it in your labs. There are open commercial source softwares which can do molecular simulations also, so you can install and do those. DL, Poly, and LAMS are some of the names. We have Material Studio, which is commercially purchased one in our lab. We do it very nicely with that. But other commercial, open source softwares, it is also possible. But let me tell you what was done. You see a carbon fiber, a toe of carbon fiber. Toe, I mean to a reel of carbon fiber. It looks something like this. It has got very, very thin multiple filaments of carbon fiber. And if you take a carbon fiber under a stem, you would find that it is actually made up of several graphitic sheets. Okay. So we started with this thought, whether if it is made up of graphitic sheets, then in terms of modeling that system, let's take a system which is made up of graphitic sheets, stacked one on top of another. Okay, so we'll assume that carbon fiber is made up of graphitic sheets. We took this, and this is what the molecular representation we did in the software. And then we also thought, this carbon fiber is certainly not very polar, so it will not get, it will not tend to reinforce my polymer. So let me make my polymer matrix polar. So what we did is we functionalized this carbon fiber. What I'm showing over here is no chemical synthesis as of now. That is the second parallel part which we were doing. But this is not straightforward. So we functionalized it using OH groups, amine and COH groups, because these are some which are very vitally polar moieties. So we did this in functionalization in some software. And then we also thought, it is not only the chemical nature of my surface which is important, but more importantly, how much rough is my surface. Because if my carbon fiber surface is rough, then it will interlock nicely with my surrounding matrix. So my thought was, let me also treat it with something which will make it rough. And one of the things that we could see of is CNT, because it's very commercially used. So we took CNT and we coated onto this. When I say coated, we actually, you look over here, we have the CNT, put on top of carbon fiber. So, and then we dispersed it into the polymer system. The polymer system was made up of polypropylene and MAG-SCBS. So I'll just try to give some details. This compatibilizer MAG-SCBS, if you look at the chemical structure, it has one arm which is polar, and it has another arm which is non-polar. So for instance, maleic anhydride and SCBS. And SCBS is interesting. The SCBS component gives you a little impactness, because this is made up of butadiene molecules over there, so ethylene butadiene molecules. It gives you a little impactness. So the thought was, for it, can it compatibilize my carbon fiber and my matrix? Can it add like a bridge in between the two? And also bring this SCBS, which will improve the impact strength of my polymer. Okay. So with all the three things, we, formulated a polymer composite. And this is what we came up with. Now the whole thing was, let me try to pull the carbon fiber out of it and see how much strength is required to do it. And that strength, if it is increased as compared to the only carbon fiber case, then my strength of my polymer composite would also increase, because now my polymer is very nicely adhered, wetted, and has an interfacial adhesion with the surrounding polymer. Okay. So with this thought, we did some simulations, and I'm just comparing the results of these simulations with you. So I've just spoken already about this. I'm just taking you directly to the results. Now this, on the left hand side, are my simulation results. On the right hand side are my experimental results. And there is a way how I can get this interfacial shear strength. And there is a way how I can experimentally also get that interfacial shear strength. Okay. I make these double shaped samples, and I try to pull that one carbon fiber which is coming out of it, and I try to pull it between the jaws of an instron, and I try to see how much energy is required to take it off. This will tell me the amount of energy needed, which is interfacial shear strength, which is IFSS. And this is similar to what I am doing over here. I'm trying to pull a carbon fiber out of the system, and I'm trying to measure molecularly through the simulations how much energy is required. Okay, I'll not go into the intricacies of this expression, but this is only trying to get how much energy is needed to pull out my carbon fiber. Okay. So going further, we did these kind of simulations wherein my carbon fiber is coated with amine, and I did several simulations with acetic acid, COH functionalization. I did several with amine functionalization, several with OH functionalization, and I tried to capture all these interaction energies. I tried to capture the interfacial energies. Now, look at the beauty of things. You may like to synthesize several of these structures, one which is amine functionalized, one which is OH functionalized, one which is COH functionalized. But over here, I just functionalize and I try to pull it out of the system. And I tell from all these results, if you look at, my amine functionalization numbers are minus 12.32 interaction energy. Now, the low, I would say the higher negative it is, higher negative means the absolute numbers. If it is 12.32, this is more negative as compared to minus 6.64. So that is the best, okay, as per the calculations. So it tells me that amine functionalization of carbon fiber is better than the OH and the other functionalization. So I don't need to go for functionalization route for the OH and the COH route. Okay, so this avoids a lot of my waste of chemicals and everything. So this is some piece of work, and which we try to find out from other things also. Now this is what the second case, where we said, no, let us try to have a coating of CNT, and what we did is, you see that CNT which is floating along with the carbon fiber, and the intention was only to bring more interlocking with the matrix. And I again try to capture what is the interfacial shear strength, what is the energy needed to pull it out. And these numbers again, if you see a CNT with amine functionalized carbon fiber, the number is the highest negative means in absolute terms very high. So minus 11.33. This again tells me that amine functionalized carbon fiber with CNT coated on it, that will be the key to it. No, don't need to make other samples. So this was the success, and then we did some of the analysis, with CNT. If you put a polymer, single polymer chain, and see whether it is, kind of interacting more with it, then so it actually, in the case of amine functionalized CNT also, this polymer matrix actually looped around automatically during the course of simulation. So this is, a formation of what we call it as a shish kebab structure. So this, polymer chain winding around the CNT is called as a shish kebab structure. So this was very apparent when we ran the simulation because of this amine functionalization and an SCBS compatibilization or MAG SCBS. This actually, rolled on it. So this was clearly indicative of that. Now, so I will not take you more into details, but this is around defects in a CNT. So CNT will have, some defects, and defects, we introduced those defects, and we try to analyze what happens. Okay, so there could be different kinds of defects, so we try to do some understanding on, there could be a stone walls defect, and there could be a vacancy defect. So in CNT, there are two kinds of defects which are possible. So we try to study, what defects will bring what impact. So we try to find that impact also. And these are the results. Okay, thank you. 5 minutes with me. And these are the results with those defect CNT structures. And through this also we could analyze which will work better or not. Okay. So these are, I would not take you more into these details. And we have done a little more analysis in terms of defects. Now, I'll just spend 2 minutes on this. Sometimes your molecular simulations would require you to make a simulation box and put some polymer chains. Now, when the polymer chains are big, the whole system is big, then your computer tends to slow down, okay? Because there are so many atoms and you're trying to understand what is the interaction of different atoms with each other. So the number of calculations is very huge, and you're not able to explore how the polymer is moving and how the polymer is interacting, so you're not able to estimate the properties. So what people do, and what we very interestingly done here, is we try to couple some of the parts of the polymer and say this whole benzene ring is not 6 or 12 atoms, there is only one atom. Okay, so we try to say there is only one atom. Okay, so likewise, what we did over here, all these dots that you are seeing over here, all these different dots, all these whole set of, graphitic sheets that we said, carbon fiber is made of. We said this whole doesn't have, 100 atoms. This is made up of one atom. And then we gave a U shape to it. And then we ran the simulations. Now, there is a way of connecting this lower level to the higher level force fields, which I'm not going in detail. But what you're essentially doing is maybe 2 lakh, 10 lakh atoms, you are reducing suddenly to only 1,000 atoms that you have to simulate and see what happens. So this is something called as mesoscopic simulations or coarse-grained simulations, wherein you have, let's say this whole galaxy of several stars, if you want to simulate, which are several thousands and billions of them, you can even do that because you have reduced, the whole set of things to one entity. This whole polymer chain, you can say, polyethylene, 10,000 atom chain is not 10,000 atoms. It is only 10 atoms. So you coarse grain the structure and say it's made up of 10 atoms. So all this we did, these coarse grain models, and we found, very interesting. So we now pulled this whole coarse grain structure out of the system, and we again try to measure the energy, how does the energy change. And we finally captured the interfacial addition energy. So these are a few things you are trying to explore what happens when the length scale increases, the number of polymer chain increases. Are the same results translating also? So these are some results, and we found similar results with this case also. Now, what I'm showing over here is the experimental part. Okay, so we try to find out experimentally whether this is working or not. What you see is we made a polymer sheets, 2 polymer sheets actually, and put 1 carbon fiber in between, and then sandwiched both the polymer sheets. And these 2 fiber ends which are coming out, we try to pull one out of it and see what is the effort needed. Okay, one case where there is only a carbon fiber, one case where there is a carbon fiber which is functionalized and coated, and see what is the energy difference. So these are some of the experimental results. Comparison with simulation, almost a very interesting and close match of the experimental, the bottom 2 ones that you see and the one over here. Those red in the experimental, this is again amine functionalized, okay? And this is again amine functionalized. So there was a huge increase, a very, very huge increase of 750% in the interfacial shear strength. Just by doing this kind of functionalization and CNT coating. You have several, you made several impacts to the interlocking of the carbon fiber and also its polar-polar interactions. So this worked very nicely, very evident from the experimental part of it. This, I would just like to say that we chose an additive which is called as hollow glass microspheres. These are nothing but core shell particles, glass. Inside it's all vacuum. And so if you add even a little bit of this 10%, the weight of your polymer will suddenly come down. So what we are trying to do is, because polypropylene will be 0.9 gram per cc, carbon fiber is around 1.4, 1.5 gram per cc. So when we add the solid glass microspheres, we're trying to compensate for that increase in weight. We are not only compensating for that increase in weight, but even reducing it further down. Because when you add carbon fiber, you are increasing the strength of your polymer, so you will have to use less and less of polymer. The thickness of your whole polymer part will reduce. So with that and with the addition of hollow glass microspheres, our specific properties were very, very high. I will just sum up all this work with one, table which I wanted to show. This table, speak about a lot of impact as compared to the first one, which is polypropylene. You just see the numbers, polypropylene, how these numbers have gradually increased, all in terms of flexural properties, specific flexural properties, tensile properties, and specific tensile properties. So a lot of impact which you can do in terms of in the engineering polymers. So these are similar results, thermal properties were improved. These were captured, and this is about the thermal conductivity part of the whole, automotive, how we can use them. They are more thermally manageable polymer products. So these are, a few more results, and XRD results, which is talking about the crystallinity, and this is how we chemically synthesized, how we saw them in SEM, and these CNT molecules which are emerging, a forest of the CNTs which were very thin. So if you see the structure, you can make out, it will definitely be interlocking very well. So these are, some of the properties, and we patented this whole formulation with carbon fibers and hollow glass microspheres. Just one thought, our study is standing over here versus several other studies which are much lower in terms of tensile strength numbers, much better than many others. But you could say that some are standing very good, but these are the other ones, commercial ones, are those which have used more carbon fiber than we have used. So essentially, this is even much better than many of the commercial ones. So this is a whole list of it, and this is where we stand versus others. So these are the summaries, and I would leave onto this slide, and thank you. And if there are any questions, I could leave. Right. I think you have a very depth, question full of depth. I don't know whether I would be able to answer you because you're trying to compare two strategies, which is, crack initiation and crack propagation. Which one would suffice, and do you need to do both of them or not? Over here, from the perspective of polymer composites, little idea which I can, present over here in terms of crack initiation. See, some of these examples which I gave here with fly ash put in polypropylene. One of the reasons why initiation would happen is at the interface of these fibers. Okay, and there are 2-3 reasons. One is there is not chemical interaction. Second is they are not very nicely interlocked. And third thing which I did not talk about, and which in this case you asking the question I would like to put up is, across these fibers, when they are mixed during shear and extruded out, at the surface of these fibers are some of the space, very micro space of air which builds up, and this is the place which initiates that crack. Now there are several people who are working on this, how this crack initiation should not happen. And one of the few of the things which I said is bring more chemical interaction or interlocking. And the third thing, which was the fly ash, we use nano fly ash in this case. And nano fly ash, what it does is it across this fiber, it goes and sits on these fibers. And when this happens, the space of air or vacuum, whichever was created around the fiber, it takes care of not initiating a crack. So we did some impact analysis also. So being a polymer scientist, I focus more on polymer, crack initiation, because we try to track, what is happening at the surface and correlate it with the impact properties or similar other properties. But crack propagation, probably, this is when you're talking about as a survey, which one should be opted and not. I would not be able to present a very good idea at this point of time. Yes. Right. Right. Closure, yes, yes, yes. 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 Right. No, you have put a very good question. Yes, yes. Sometimes what happens is, many of these additives which you add, let's say you add nanosilica or, where you have polymer intercalated or exfoliated across the layers of silica. One of the reasons is that, when this crack is started, the polymer is the first target. And when this will hit these, I would say the ceramic layers of silica or any of the other additives, it will try to stop them. While people talk about using a lot of these additives, natural fibers, or some of the other ones which I mentioned, one of the intentions is also can it stop the movement of the crack, and which it will do because you have actually kept something in between that crack, and polymer is the softer material relatively. So, but I think lot of people are now doing it naturally, and multiple additives which are being added with the intention that the crack initiation should reduce and crack propagation should also reduce. And the examples and the 3 things which I talked about were more focused on the initiation, but many of these additives automatically they take care of the propagation because polymer is there. So there are several things, but yes, people are targeting both of them, but which one should be taken in terms of the survey side? I think right now I don't have a very good answer to it. Thank you.
Thank you, sir, for sharing your vast research experience with us. On behalf of the organizing committee, I request Dr. Madhu, HOD Department of Chemical Engineering, RIT, to hand over a memento as a token of our appreciation and respect. Thank you, sir. We'll move on to the second plenary session for the day. So I take privilege in introducing the second plenary speaker for the day, Dr. Sunny Jafar. He's working as Associate Professor in School of Mechanical and Materials Engineering in Indian Institute of Technology, Mandi. He got his MTech and PhD degree from IIT Roorkee and BTech from Punjab Technical University. And he got various awards into his credit. He got Young Researcher Award 2023 from IIT Mandi, Faculty Teaching Honor Roll Award 2021 from IIT Mandi, Early Career Research Award by SARB 2017 by DST Government of India, PhD Scholarship MHRD Government of India, MTech Scholarship MHRD Government of India, and his areas include advanced manufacturing processes for polymer composites, sustainable biocomposites, recycling of polymer composites, surface engineering, and experimental tribology. He got 3 patents into his credit, and he has published various research articles and papers, and he has completed various research and funded projects, including SARB and DRDO. It's great to have you with us today, sir. So I request Dr. Nagaraju Kottam, sir, to welcome him with a bouquet. So now I request you to take over the dais.
Yeah. Fine. So good afternoon to all. So at the outset, I would first like to thank the organizers of this conference to invite me here, and I'm really honored to deliver this invited talk. So as you can see, the title of my talk is regarding use of microwaves in manufacturing and recycling of advanced polymer composites. So at IIT Mandi, I also lead the Composite Design and Manufacturing Research Group. So where our group is basically involved in manufacturing and also designing the composites, structural composites, particularly for various applications like aerospace, wind turbine blades, etc. We use advanced finite element analysis in-house codes. Of course, we also use the commercial finite element softwares targeted towards composite materials and their use in various structural applications. Additionally, we are also utilizing microwave energy to manufacture the composites. So we'll see some details about this work in the next few slides. So before I begin, I would also like to acknowledge some of the work that I will be showing here is done by my 2 PhD scholars, Rajiv and Manjeet at IIT Mandi. So before we go into the technical things, a quick 2 minutes on what about IIT Mandi. So many of you may not be knowing IIT Mandi, or you may be knowing still about it.
So IIT Mandi is basically a second generation IIT established by Government of India, and it is situated in this Himachal Pradesh, in the district Mandi. So the campus is situated 15 kilometers away from the main city. So we are outside the hustle and bustle of normal city life. And for me, it is quite a change whenever I'm coming to Bangalore, because it's completely opposite for me. So our campus is spread over 520 acres in this forest and mountains and rivers. It's all like that. And we have cold winters. You can see snow on our campus, extremely cold. In fact, this image, if you see, is of February, this year's February, where all these mountains are in a lot of snow, and it's extremely chilling during winters. So fortunately, we have long winter vacations. So it is opposite for us. We have long winter vacations, short summer vacations. Other than this, our campus is situated at an approximate altitude of 3,000 feet, or it is around 1,100 meters, which makes it quite pleasant during summers, but of course, winters are much harsher. The campus is spread in these two parts. We call it North and South campus. So here you can see this is basically the South campus and the North campus. Now we are also connecting both of the campuses. So I'm here since 2016 and seen a lot of campus development since then. And now coming to the just outline of my talk today. So I'll bring it from a little basics, because many of you may not be knowing composites, or many of you may be knowing details about composites, but we'll start with a little basics. We'll be spending some time on knowing basics on microwave processing, and we'll see how they are being used to manufacture some of the structural composites with glass fibers and carbon fibers, and how the microwaves have been used to recycle the glass-based fibers. So composite materials, as my previous speaker, Dr. Gaurav, also spent and emphasized. So these are basically unique materials, multi-phase materials with two or more group of materials which are combined at a macroscopic level. So they are not combined in a microscopic level, which gives them a unique set of properties. And we can tailor these properties as per need. So in general, in any structural composites, specifically speaking, we have two components, which is the matrix as well as the reinforcement. And broadly based on the matrix, the composites are classified based either polymer or metal or ceramic. So composites are not new. In fact, nature has a lot of examples to us from the composites. All the wood that we see is composite made consisting of lignin and cellulose primarily. Our bones are also composites. All these honeycomb structures are also based out of composites. Now, structural composites, as my talk is more focused upon, structural composites are more used in applications where lightweight properties are desired with high strength. So all these applications where we have the aerospace structures, like the structural parts of airplanes, be it military aircraft or commercial aircraft, all the electric vehicles that we see around or will be seeing around in coming decades. Of course, the internal combustion vehicles are also utilizing a lot of composite parts, but it is the electric vehicles that are going to lead the front of composites, where we want the electric vehicle to have a longer range. So again, composite materials are the go-to materials. And not only that, composite materials, they are also used in several other applications, prosthetics and some furniture, etc. and so on. This type of pressure vessels, fishing rods, etc. So if you see the use of composite, why composites are so popular. So composites are popular because of some of the important properties like their weight, thermal expansion, stiffness, and fatigue resistance when compared with the monolithic metals like steel and aluminium. So given all these attractive properties, they find widespread applications as just we discussed. Other than this, composite materials, they also have a lot of advantages. I'm not going to spell each of them out. And at the same time, composite materials, they also have certain limitations. So our research group is focusing on addressing specifically these two limitations in composite materials, specifically polymer composite materials where we have long process cycle times. And because of that, we have certain manufacturing difficulties that arise from this. So what I mean by cycle time is the total time it takes to make a composite part, starting with the assembling the fiber and the matrix and so on, and then the time it takes to cure the resin and then get the final product out. So although there are other limitations also there with the composite materials, and these limitations basically they open up scope for more research. I mean, all these are basically research problems. So you can look at it in that way, and each of it has a lot of potential scope to taking it further. But in this talk for this today, we are just focusing on the cycle time issue. So the structural composites specifically that we are dealing with mostly are revolving around aerospace and wind turbine blades in particular. And of course the electric vehicle, yes, just I mentioned though. So this here basically what I'm showing is the structural parts of the vehicle which are made up of the composite material, which include this engine hood, fenders, pillars and so on and so forth. So composite materials, again, I will not spend much time on these slides as these are also a very basic slide where the classification on composite materials is being presented based on the type of reinforcement. So based on the reinforcement aspect ratio, it can be either particulate type or fiber type, and based on the fibers, you can have single or multiple layer fibers and so on and so forth. Again, what we are dealing here is with the laminated composites today and having bidirectional fibers. So in all the manufacturing techniques that we have for the structural composite, the industrial techniques which are used, so they basically are again revolving around either it is the matrix is thermoset or thermoplastic. So essentially it is the behavior of the polymer towards heat that in thermosets we cannot remold it because of the permanent crosslinks. And thermoplastic, of course, we can remold it multiple times. So just to imagine, thermosets are like cake. Once it is done, baked, you cannot do anything about it. Thermoplastics are more like an ice cream where you can melt it, again you can freeze it and so on and so forth. So based on this, these are some of the existing techniques, existing technology in industry which makes composite parts using these things. And specifically speaking, here we have utilization of prepregs in structural composites, especially in aerospace, and then we have sheet molding compounds and bulk molding compounds being utilized. Now here, all these techniques, they basically utilize a conventional source of heat, where heating is done using some heat source. And if you look at the basic of all these techniques in manufacturing, so essentially these 4 steps are followed where we have impregnation, layup, consolidation and solidification. So impregnation is basically when once the matrix is wetting out the fiber, just to ensure the matrix is completely wetting out the fiber for proper interfacial bonding. Layup is once we stack up different layers and different orientation of fibers to get quasi-isotropic type of a composite. Consolidation is once we apply pressure to remove any air gaps and to have a proper bonding between various lamina layers, and then heat is applied. So here is where the things change now. Now heat application can be done using various means as shown here. But in our work, we are utilizing microwaves as the source of heat. So microwaves, as you know, are basically electromagnetic radiations which are available in the frequency range of 0.3 to 300 gigahertz. But microwaves were initially invented more for communication purpose. So for heating purpose, it is these specific frequencies like 433 megahertz, 900 megahertz, and 2.45 gigahertz, which are reserved for heating purpose. So if you take any microwave, be it kitchen microwave, so it will be operating in India, say at 2.45 gigahertz. So a particular frequency is fixed for heating purpose. Other frequencies in that broad range are for communication purpose. So this is done so that there is no overlap between the frequencies which are used for different purposes. So microwaves basically are non-ionizing, coherent and polarized type of electromagnetic radiation which can be transmitted, absorbed, depending on the type of material. So what I mean by type of material is the dielectric properties of the material, the dielectric response of the material. So based on this, we'll see some classification of the materials here. So how microwave heating is done? So microwave heating, if you will observe, is completely opposite to conventional heating. So in microwave heating, basically, it is the conversion of energy. So if you see here, basically we are comparing conventional heating with microwave. So in conventional heating, you can see that heat transfer takes place from source. That is, source is some sort of heating element placed around the target. So the bigger circle is basically the target and smaller circles are the heat source. So based on the conventional modes of heat transfer, the convection, convection or radiation, the heat may be transferred. So outer surface is generally at higher temperature compared to core, and it takes a good amount of time to have the whole of the target material at uniform temperature. This issue especially becomes more challenging once we are dealing with polymers which we know are poor conductors of heat and electricity because of the covalent bonding. So there are shared electrons, so no electrons are free, because of which this difficulty arises. So in microwave, basically what happens, there is energy conversion. So no heat is transferred, rather the heat is generated within the material based on the dielectric response. So we observe an opposite temperature profile here. So there are certain advantages associated with this, which can be summed up here as cost saving, low cost equipment, volumetric heating, and all these things are there. In fact, the research work that we started was with a kitchen microwave of 25,000 rupees only back 7-8 years back, and with that sort of ease, we also understood more details on heating. So it is basically the two mechanisms that operate in microwave field, that is polarization or ionic conduction. So polarization is basically the polar molecules once they are exposed to microwaves, how they align themselves with the alternating field. And this basically occurs at 2.45 gigahertz. And this alternate movement of the polar molecules under the influence of electromagnetic radiation generates a frictional heating inside the material. So this frictional heating is then basically rise in temperature takes place, because of which, and consequently we say heating is happening. Ionic conduction is another mechanism, but it is more popular at lower frequencies of the order of 900 megahertz. And for our work going forward, we are focusing more on polarization, because the frequency of microwave being utilized is 2.45 gigahertz. So based on the materials, interaction with the microwave, so materials are classified as transparent, opaque, absorber or mixed absorber. Transparent means it is transparent like glass is transparent to visible light, so it can just pass through, no interaction, no heating, nothing. So selected materials based on their molecular structure become transparent like Teflon, quartz or alumina up to certain temperature of 600 degrees Celsius. Then certain materials are opaque, like the bulk metallic materials. It is also always advised not to use the bulk metallic materials inside the microwave, like fork, spoon, etc., because it may cause a reflection of the microwave. Because of the crystalline structure of metals, the skin depth is extremely low, because of which the microwaves, they bounce off from the surface. So it creates a localized plasma, because of which arcing is seen or sparking is seen. Then we have absorbers, where the material can absorb the microwave and heat up. Here, water is one of the popular material, and all our food, why it gets heated up in the microwave is because of the presence of water. All our food, whatever we cook or we eat, has a significant portion of water, and that helps in heating. Other than that, silicon carbide, charcoal is some other absorbing materials of microwave. Lastly, we have mixed absorbers, which are basically multi-phase materials. Like composite materials, they come in the category of mixed absorber, where one phase, that is either the matrix or the fiber, can be absorbing, or it can be vice versa. Means, fiber can be transparent, matrix can be absorbing. So based on that, we have this classification, and this classification is important to also understand because once we develop the tooling for manufacturing, so there the selection of material has to be done considering these aspects. So modeling of microwave processing is also another important area where this process can also be modeled to estimate the temperature range, because practically speaking in bigger microwave ovens, theoretically we speak the uniformity of electromagnetic field, but in many cases there are presence of hot spots which needs to be minimized, and modeling and simulation is one of the useful tool. And this modeling is based on certain aspects of dielectric properties where we have the presence of real and imaginary parts. And for polar molecules, these real and imaginary parts are expressed as follows. In microwave, generally the temperature dependence is based on this exponential term, so which is also a function of activation energy. And here what you will observe that this temperature rise is a exponent function, which means temperature rise is very quick. It is an exponent function, means the rise is quick. And for non-magnetic materials, this heat balance equation, heat generation equation is shown where it is again a function of root mean square of the electric field. The magnetic field has no role to play with non-magnetic materials, which is polymers in our case. And by plugging in the value into the heat balance equation, we can derive the temperature distribution and estimate where hotspots are forming and where they can be avoided. So using all this background, now I'll just show you the work where the use of microwaves is done for manufacturing of carbon fiber composites. So this work was sponsored by Aeronautical Research Development Board, DRDO, in one of the projects, where the goal was to manufacture certain carbon fibers and compare the carbon fiber manufactured using microwave route and the conventional route, what properties, especially the mechanical properties were looked at. Carbon fibers based composites, as you know, are one of the popular composites in aerospace application for various structural parts. So all these parts of the aircraft, they are made using this. And carbon fibers, because of their unique molecular arrangement in the graphitic rings, where you have strong covalent bonds between these carbon-carbon atoms, and particularly these bonds, they get aligned along the longitudinal axis of the fiber, because of which they are able to exhibit very high properties, especially in the loading, like stiffness, strength, and so on and so forth. And because of which they are very popular. And for structural composites, we use carbon fiber in this type of fabrics, which are woven fabrics in different weave forms. So in our work, what we did is basically, again, issues of research are basically to look how to minimize the curing cycle time, at the same time maintain the properties that we get with the conventional manufacturing route. Because we are dealing with polymers, and polymers we know are basically poor conductors of heat. So here, processing with microwave is also not straightforward, especially with carbon fibers, because carbon fibers are also conductive fibers. They can conduct electricity and heat as well. So generally, if you will place carbon fiber in microwave field, so you will observe arcing very similar to what we observe in case of metals. So it becomes important to basically tackle that issue by grounding the charge on the surface of the carbon fiber. So we did that in the setup that we have developed, that just I will show. So this is basically the results, just I am showing the preliminary result once you mix the carbon fiber with an epoxy and hardener. And if you directly expose it with microwave, in the microwave, so we could observe the non-uniform heating because of hotspot presence. And this ended up with some defects on the carbon fiber composite. So what we did is basically we took these materials in the work. So we have used carbon fiber mats of plain weave in the plain weave configuration, and the epoxy as bisphenol epoxy mixing with the hardener. So here we have developed this setup where we are utilizing the mold. This is an open molding process where we are using a PTFE mold. So PTFE is also a microwave transparent material, and we have putting up the vacuum bagging arrangement on it. Additionally, we are also we also planned here to introduce the thermocouples to understand the temperature distribution while the microwave curing is being conducted across various layers. And the carbon fiber plies, they were also grounded using the aluminium tape here, which grounded all the charge. So we eliminated the charge by introducing this aluminium tape and earthing it out. And all of this arrangement was placed in an industrial microwave applicator, and the rest of the vacuum bagging arrangement was used. And here, what we observed upon this comparison was done with thermal curing. So wherein we proposed this sort of the heating mechanism, where in case of carbon fiber based composites, this is basically heating done at both the levels, that is the heating of the carbon fiber, because carbon is known to absorb also if managed properly. And epoxy, as we know, is a polar molecule which also has significant dipole moment, because of which heating takes place. And because of all these properties, we could observe that in this case, the degree of cure was also estimated using the residual enthalpy, and we observed in microwave. Actually, the experiment was done at various microwave power levels, shown here at 180 watt, 360, 540, 720. And T basically is the thermal curing, where the degree of cure in case of microwave was much higher, especially at lower power levels. Then we also compared the mechanical properties, and in certain cases like the 360 watt, the mechanical properties were better in terms of tensile strength and elastic modulus. So similar trends were also observed in case of flexural properties. This is using 3-point bending test. And in these cases, you could observe the microwave exhibited better properties. So then we also did the energy comparison by connecting an energy meter in series with both the setups. I will also show the photograph of the setup, wherein we also captured how much energy goes into making the same sample size at the lab scale. So with microwave, it was very less. It is almost 11 times less to what it was observed in case of thermal curing. So what it was in thermal curing, and time was also significantly reduced. So that is how we could establish that using microwave we can reduce the time of curing as well as the thermal curing compared to thermal curing. So the similar setup was also utilized. I just quickly walk through in case of glass fibers. So glass fibers are also another sort of reinforcement used in various structural composites. Just I will quickly go through as I am also reaching my time limit. So the only difference here in case of glass fibers when compared with the carbon fiber is glass fibers, they do not interact with microwave. As carbon fiber was interacting with microwave, glass fiber are transparent to microwave. So here the curing is entirely dependent on the epoxy's dipole moment. So the epoxy, as it is polar, so it is ultimately heating is taking place because of the in the epoxy, of course, when heating is taking place, so this heating basically initiates the cross-linking and how the composite is developed. So in this case also similar studies were conducted to estimate curing time as well as the comparison with the thermal curing. So we compared the densities and wide volume fraction. In case of microwave, the wide volume fraction was less at perhaps low powers, but of course at higher powers because of non-uniform heating it was higher. But at lower powers we can say that, say in case of this case, the 540 watt was the best, where we had 3.8, and in case of thermal curing it is still 6.2. So we also estimated the glass transition temperature. That gives an idea of how much curing is taking place. So it was best in case of 540 watt. Similarly, curing cycle time was significantly less compared to the thermal curing, which is 8100 seconds here. And properties, mechanical properties were also better, of course, at optimized condition, that is 540 watt. So energy consumption analysis also shows similar trends, and what we can conclude is that microwave is good for manufacturing as for these type of composites. So now these are basically the setups which are developed in our lab at IIT Mandi for basically manufacturing both the glass fiber as well as the carbon fiber composites. But the another important work that we have done is towards recycling because that is also very important because composite parts are being used in several applications, but the recycling of the composites is much challenging because in multi-phase materials it is difficult to separate out the two components once they reach the end of their service life. So here again we try to use composite material, this microwave to minimize the or recycle the composite glass fiber composite waste. So this is just a background data which just shows you how the use of composite material is going to get more and more, especially in these sectors which have the automobile, aerospace and wind turbines. So both consumption of carbon fiber and glass fiber is going to get increased in the coming years. So as of now, what is happening that this amount of waste is getting generated and it will be generated in coming time. So we need to do something to tackle this waste. So what can be done is basically again the concept of reducing waste, reusing it, reducing the size, recycling and so on. So in recycling also what is happening that we are basically converting the waste material into new materials. So recycling basically helps to minimize the negative effects of these materials. As of now what is happening, it is just most of the material is shredded and put into landfills, and because as it is put into the landfills, it causes a lot of environmental issues like reducing fertility of land and so on. And as in most of the structural composites, it is the epoxy which is used as a resin or the matrix. So it practically does not break down because once it is cured, so it is there forever. And because of which it releases several harmful chemicals not only into the air but also groundwater pollution takes place. So a lot of recycling methods are already available which include these methods like mechanical waste where we shred it into small parts, thermal waste where we pyrolyze it, chemical waste, microwave pyrolysis is also there. To this what we have added is a combination of microwave heating and chemical processing. So wherein what we have done is basically, I'll just skip through in the interest of time because these are the established things. I'll just come to what we have done. So in case of our work, what we have done is we identified the limitation of the existing methods which included reduced fiber length, introduction of more surface defects, high cost and so on. So what we did is basically we utilized the microwave energy in case of heating and use of these chemicals that is acetic acid and hydrogen peroxide. So a specific combination of this hydrogen peroxide and acetic acid was utilized in presence of microwave to break down the epoxy. And this epoxy gets dissolved and after which we are able to recover back the fibers. So now the chemical level things is basically was taken care by one of my colleague. It is a part of an interdisciplinary research. A colleague from chemistry had taken care of that, how this chemically it happens. But the use of microwave to break it down was then attempted and after cleaning it we could recover the fibers back. So as of now, we filed an Indian patent, we also got the patent granted. And after that, we published some papers where we proposed this mechanism. Of course, I don't know more technicality about the mechanism because it is a purely chemistry-based approach where, of course, my colleague helped me out in this, where in this was proposed and it got accepted. The crux is basically the breakdown of the epoxy network here and by generation of some radicals. So these radicals help to break down the epoxy structure because of which we can able to dissolve the epoxy. Of course, we also conducted the decomposition efficiency with this and we could observe around 97% of decomposition and we analyzed the fibers after the decomposition or recycling. So we tried out number of experiments and at certain experiments we compared the properties with the virgin glass fiber. Virgin means unrecycled glass fiber. So we could say that in some cases properties of more than 90% were achieved compared to the virgin glass fiber. So we also analyzed the fibers using scanning electron microscope just to look at what quality of surface of the fibers we were getting. So in certain cases, as you can see in figure D, E, and F, some of the epoxy did not dissolve. Of course, at optimized condition, we could completely dissolve it. So the work is only shown here up to the fiber part. And here we could say that by using this ratio of hydrogen peroxide and acetic acid in 30-70 to 50-50, in microwave at 720 watt at 180 seconds, we could decompose at approximately 97% of it. Just what's not presented here is we have also tried out with carbon fiber, and we are getting similar results. Of course, the data is not published yet; it is in process. And this type of work has gathered a lot of industrial attention, and we are in talks with certain industries for TOT, that is transfer of technology, wherein the recycling work of fiber reinforced plastics can start in India. Because in India, we are already struggling with single-use plastic, and we are using going to use a lot of composites in coming time. So this type of work, some of the industries are in talks with us for commercializing it, taking it to the next stage, and by using a TOT, we will be able to do that. And all these things, again, recycling, and of course, as Professor Gaurav mentioned, upcycling can also be the next phase where we can use such type of fibers to create new composites. So, of course, whatever work we did, it's not that end of thing. There are always limitations to what we do in an academic institute. So, scalability, of course, we tried out everything at a lab scale. So, at commercial scale, there will be some unprecedented challenges which need to be taken care of. And high investment cost may be incurred because microwave technology for India is new, but abroad in several places it is being utilized for manufacturing of composites and even recycling. And in India, as we still have a limited regulatory framework, that we don't have more framework to assist in this type of work. So this all will be there in coming times. So this work actually gathered a lot of traction in media and elsewhere, and we got so many industry contacts were established because of this. And we are hopeful that we will be able to transfer this technology for this important thing on recycling of the composites. So that is all with the references and so on. So if there are any questions, I will be happy to answer. Thank you. Yeah? Yeah. Yeah, so actually in scaling up, the challenges that we see is mostly what size of the part, mainly the size of the part which can be managed. Like we are here targeting, say for, if we ideally target for wind turbine blade, which has a lot of composites, lot of fibers. So size of those components is extremely large. So tackling the recycling part inside a microwave field, that is a very significant challenge. Of course, for smaller parts, it can be managed using a reactor, but for larger parts, it will be a challenge. So I see that as a big roadblock. Yeah, so globally there are big microwaves as big as to completely cure an aircraft wing. So Airbus is already using this technology in Germany to get the parts for aircraft. And in South Korea also some companies are using for recycling work. But again the question is on how big the size. Of course bigger things need to be brought into manageable sizes, but it will not be as small as the current shredding things are being. Yeah. A conveyor type of process can definitely be tried out. No. Boeing is not using continuous, so in fact they are using a closed door sort of big microwave. But actually that they are using for curing. So curing is much simpler to handle because no liquids are involved. But in recycling, these liquid chemicals are involved, so continuous process could be a better. No. Currently no. Yeah. Yes. with all the precautions, especially the quality of fiber that we are getting. It is very near to the virgin properties. So we don't claim that it can be used in the similar application, but with the scale down application, it can definitely be reused. Like carbon fibers are very expensive to manufacture, and recycling those type of strategic materials could be helpful for upcycling it into some different product. Yeah. Yes, yes. Yes, yes, yes. Yeah. Yes.
In the market also.
Yes, yes, yes.
Now in the market.
Yeah. How we can scale it up? Yeah, yeah. Scalability is a thing. Yes, yes. Yes, yes. Yes, yes, yes. We are in talks with certain industries to how to scale it up, and if that is successful, then TOT can be attempted. Yeah, yeah, yeah. Thank you. Thank you all. Yeah. Thank you.
I request Dr. Bharat Bhushan, Professor Emeritus from the Department of Mechanical Engineering, to hand over a moment the token of our appreciation and respect.
Very unique work, Professor. Thank you. Yes.
Now we will move on to the third and the last plenary session for the day. I would like to introduce our speaker, Dr. Jyotish Kumar Parameshwaran Pillai. He is Professor and Director, Center for Excellence, Alliance University in Sophisticated Test and Instrumentation Center. So Dr. Jyotish Kumar Parameshwaran Pillai has postdoctoral research experience at Leibniz Institute of Polymer Research, Dresden, Germany, and Catholic University of Leuven, Belgium. He received his PhD in Chemistry, Polymer Science and Technology from Mahatma Gandhi University, Kerala. Dr. Jyotish Kumar has published many papers in high-quality international peer-reviewed journals on polymer nanocomposites, polymer blends and alloys, and biopolymer. He is a frequent invited and keynote speaker and a reviewer for many international journals, books, proposals, etc. He has received various awards and recognitions, including the prestigious Inspire Faculty Award 2011, Kerala State Award for the Best Young Scientist 2016, and Best Researcher Award 2019 from King Mongkut University of Technology, North Bangkok, Thailand. Dr. Jyotish Kumar is named in the world top 2% of the most cited scientists in single year citation impact 2020 by Stanford University. His research interests includes polymer coatings, shape memory alloys, antimicrobial polymer films, green composites, nanostructured materials, water purification, polymer blends, and high performance composites. Sir, we are happy to have you here, sir. I request Dr. Nagaraj, sir, to hand over a bouquet. I request you to take over the dais for the session.
So good afternoon. Myself, Dr. Jyotish Kumar. I am from Alliance University. I am heading our instrumentation center there. So today I will talk about some of the applications of nanotechnology. So in this lecture, actually I am planning to give an overview of what we have done, I mean myself and my team, over the last 15 years. So before going to the applications of nanotechnology, so I think we should always remember the names which are famous, you can see here. You can see here the photograph of Richard Feynman. So he is considered as the father of nanotechnology. In 1960, in one of his lectures, he talked about the importance of nanoparticles. He told the people attended that conference, there is plenty of room at the bottom, there is plenty of opportunity at the bottom. So that's why we consider him as the father of nanotechnology. If you consider the term nano, you can see it is a Greek word that is nanos. So nanos means small man. So that is how this name came, nanos. And why we are interested with this nanoparticle? There are different of reasons. And if you look at this nanoparticle, they are approximately maybe suppose if the particle size is 1 nanometer size, so that means it may contain approximately 10 atoms. And all these atoms are at the surface of the nanoparticle. So suppose if you take a nanoparticle, and that is 1 nanometer in size, and you can see all the atoms are, it is approximately there may be 10 atoms in that nanoparticle, and all the atoms are at the surface of the atom. But that is not the case with bulk material. If you take a bulk material, all the atoms are at the interior, but that is not here in the case of nanoparticles, where all the atoms are at the surface. That is one of the, therefore the functionality will be totally different. So bulk material functionality is different, for nanoparticle functionality is different. One of the reasons is this factor. And the second reason is surface area. So surface area of nanoparticle is very large when compared to that of bulk material. So you can see an example here. So you can see one brick, you can see the schematic here. So one brick is approximately 6 centimeters square, that is the surface area. And suppose if I cut that brick into 8 small pieces, then you can see the surface area increases to 12 centimeters square. And on the other hand, if I divide it further into 64 small pieces, you can see the surface area increases to 24 centimeters square. So that means when you move from bulk material to nanoscale, the surface area increases. That is one of the reasons why we are interested with nanoparticles. So these are the two basic reasons why people are interested with nanomaterials. One is their surface area, and the other one is surface atoms. and therefore their functionality will be totally different. If you look at the classification of nanomaterials, again you can see we have three different types of classification. One is carbon-based classification, carbon-based, and then you can see inorganic based, and then you can see polymer-based. These are the different classifications of nanomaterials. If you look at some, you can also see some of the examples here. If you look at the classification for carbon-based, you can see fullerene or buckyball. And then you can see graphene there. You can also see graphene, carbon nanotube, etc. And so you can see we have fullerene there, we have graphene there, we have carbon nanotubes. And then if these are examples for carbon-based nanomaterials. And we also have inorganic nanomaterials. For example, metal-based nano, for example, metal or metal oxide, gold nanoparticles, titanium dioxide, zinc oxide, silver nanoparticles, etc. All these are examples for metal nanoparticles. And again, we also have polymer-based or organic-based. You can see polymeric nanomaterials, you can see liposomes, etc. All these are examples for organic-based nanoparticles. So we can make use of these nanoparticles and we can put it in polymer and then you will get polymer composites. And again, in polymer composites, we can use bulk materials as well as nanomaterials. I already told the nanomaterials, the functionality is totally different. Therefore, when you put these nanomaterials in polymer, the polymer composites will perform in a different way. That's the reason why people are interested with the nanomaterial. Not only in polymer composites, there are different of applications. We can use it in solar cell. In my laboratory, we make polymer films for food packaging applications. We are interested with polymer coatings. We are interested with polymer composites. We are interested with conductive films, etc. Now, this is actually a small, classification of nanomaterials. We can classify these nanomaterials into three zero-dimension, where all the three dimensions are the nano range. For example, fullerene, you can see the example there. And then we have one-dimensional nanomaterials. We have the carbon nanotube. Then we have two-dimensional nanomaterial. We have graphene. And then finally, we have three-dimensional nanomaterial where we have graphite. This is a simple classification of nanomaterials based on the dimension. If all the three dimensions are nano range, then we can have the fullerene as an example or buckyball. And then coming to the history of nanotechnology, I already told that we have Professor Richard Feynman in 1959. He told the people that there is plenty of opportunity at the bottom. And that's why we consider, this nanotechnology is actually a new area. It was, came up after 1990 only. So it is approximately 30 to 40 years old, this area. But you can see approximately 60 years before, Richard Feynman told the people there is, these nanoparticles are there and there is more possibility with these nanoparticles. And you can also see, William McLean. William McLean is actually an engineer. He also attended that conference. And you can see the photograph there on the other end. You can see William McLean and Richard Feynman. You can see the photograph there. So, this William McLean is actually an engineer, and Richard Feynman asked him, can you make an motor, nano motor? Then he take up the challenge and he make this motor. You can see the photograph here. So you can see here. And then we have, in 1974, Norio Taniguchi is a Japanese professor. He coined the term nanotechnology. And then we have Professor Tsujimo Lima, and he invented carbon nanotube in 1991 along with Professor Pulikal Ajayan. You might have heard about Pulikal Ajayan. He is from Kerala. He is now in Rice University, and they made together carbon nanotube. And then you can see in 2006, Jennifer West and Naomi Hallis, they learned that we can make use of these gold nanoparticles for cancer treatment. approximately some 20 years before, they found out that we can make use of gold nanoparticles for cancer treatment. But if you look at, we cannot use directly these gold nanoparticles for cancer treatment because gold nanoparticles are highly toxic. That's why not that much development in that particular area because of the toxicity of gold nanoparticles. And then we have in 1985 we have Rice University researchers. They make this fullerene. And then we have in 1986 Eric Drexler. So he wrote a book that is based on nanotechnology. And then Civics is the first company for nanotechnology. And in 2005, Professor Gundar, he coined the term nanotoxicology. So nanotoxicology was coined by Professor Gundar in 2005. He is from United States. Now one can see nanotechnology in nature. For example, lotus leaf. If you look at lotus leaf, if you look at this photograph, you can see the water droplets are rolling over these lotus leaves. So this is because of the nano spikes that is actually present in the lotus leaves. So this is one such example where we can see nanostructures. Even we could find nanostructures in our nature. Then you can see we have the wings of the flies. So if you carefully look at the wings of these flies, you can also see, unfortunately it is not working properly, you can see the contact angle here. This contact angle is 71, and you can see the contact angle is 151 here, and this is 126, this is 157, this is 140, and this is 168. So contact angle actually represent the hydrophilicity as well as hydrophobicity of the surface. So one can find out whether the surface is hydrophilic or hydrophobic by looking at the contact angle. If the contact angle is less than 90, we can call the surface as hydrophilic. Hydrophilic means water loving. On the other hand, if the contact angle is more than 90, then it is hydrophobic, that is water hating. So if you look at the contact angle of these are actually all the same images of the wings of these flies. So you can see different flies here. You can see the same images, or 10 images of the flies you can see here. And you can also see the contact angle here. You can nicely see the nanostructures. In all these wings you can see the nanostructures. And also you can see the surface hydrophilicity or hydrophobicity. And this is actually terminate where the contact angle is 71, that is water loving. So that's the reason why this terminate fly cannot fly when it is raining. If it is raining means it will become wet. This surface of the fly will be definitely wet because of the contact angle here, it is 71. But on the other hand, if you look at the rest of the flies, their surface contact angle is more than 90. So it is fully hydrophobic or water hating, that's why they cannot fly even if it is raining. So in one way or other way, one can find these nanostructures in our nature. Even in our flies, we can see nanostructures if we carefully look at the wings of the fibers with the transmission electron microscopy images. So this is how we usually measure the contact angle. This is actually a contact angle meter. By putting the sample here and putting this water droplet over the surface of the sample, one can measure the contact angle. Now you can see in butterfly, we have very nice colors in butterfly. Why these nice colors in butterfly? Because of these nanostructures. So you can see, this is again a tape image of this surface of the butterfly, surface of the wings. So you can see very nice patterns, nano patterns. So because of these nano patterns, we have diffraction of light. And this diffraction of light is actually responsible for the nice different colors of butterfly. Again, gecko toes. If you look at gecko toes, again you can see the term images here, approximately 100 nanometer. You can see here the resolution, maybe some 50,000 or 1 lakh times. So we can see very nice nanostructures in the toes of this gecko. So that's the reason why it can climb over anywhere. And then if you look at the shark skin, so in shark skin also we have nanostructures, and this nanostructure is actually responsible for preventing the bacteria and algal growth over the surface of the shark. So one can find nanostructures over the surface of the, over the surface of, in our nature itself we can find nanostructures. Now again another example you can see here. This is actually a water strider. Water strider can easily walk over the water surface, again because of the nanostructure that is actually present in the legs of the water strider. And again, peacock feathers, very nice different colors in peacock feather is again because of the nanostructures that is actually present in the peacock feather. And then if you look at the history, ancient times, our forefathers make this kind of nanomaterials or nanostructures. But they don't know that it is nanostructure because we don't have any sophisticated instruments at that time to look into these nanostructures. Now we have transmission electron microscopy, now we have high resolution system, now we have confocal microscopy, now we have atomic force microscopy to look into the nanostructures. At that time we don't have. But you can see this is actually a Roman pressure. So you can see this is actually a Roman pressure that was made in AD, approximately AD 400. And if you look at the color, it is green in color. This is made up of glass, green in color. So suppose if you pass light through this Roman pressure, this is Lysoglass cup, and you can see the color of the green color become bright red. This color change is actually due to the presence of nanoparticles that is present in the glass. So in this cup is actually made up of glass, but it contains some nanostructures. This nanostructures is responsible why it shows different color when you pass light through it. So you can see the brilliant color, and it also contains glass silver alloy. The silver glass alloy is actually there in this glass, and that is responsible for this color change when you pass light through it. And also you can see the Mayan blue. So we are using different types of paint for difference of coating application, and maximum lifetime is actually for 3 years, maybe 5 years, or maybe 10 years. But if you look at this Mayan blue, you can see this is actually high resistant pigment, this Mayan blue. And it can survive for thousands of years. That is the advantage of this Mayan blue. And the scientists learned that because now we don't know how we can make this Mayan blue. But scientists found that it is actually a combination of indigo dye. You can see an indigo plant here, indigo dye and clay, nanoporous clay. So a combination of nanoporous clay and indigo dye is actually the responsible factor why this Mayan blue is highly resistant. And then if you look at Damascus steel, it has very high or very good shatter resistance. So the high shatter resistance is actually again because of the nanostructures actually present in Damascus steel sword. And then if you look at the pottery at Mediterranean region, again you can see the glazing here. So glazing is actually because of the nanostructures or because of the nanoparticles. So these nanoparticles is actually responsible for the glazing in the pottery. This is like Mediterranean region. Mediterranean region means African, European part, near to Sweden and all. And then coming to synthetic nanoparticles, you can see we have different types of nanoparticles are available. And I have shown some of the photographs here. This is scanning, this is TEM images of multi-wall carbon nanotube. You can see multi-wall carbon nanotube here. And as I already told, these nanoparticles are too small to see with our naked eye. We cannot see with our naked eye. So in order to look into these nanoparticles, we need sophisticated instrumentation. And this is transmission electron microscopy images of multi-wall carbon nanotube. And this is again transmission electron microscopy images of graphene. And you can also see some micro containers here. This kind of micro containers we use in our laboratory for painting applications, for self-healing applications. And then this is titanium dioxide, metal nanoparticles, and you can also see copper nanoparticles there. And also we have an alloy-like particle. So different types of particles one can, we have different types of, we have metal nanoparticles, we have graphene, we have carbon nanotube. So all these usually we bought we used to purchase this and we put it in the polymer. And this is again another type of nanostructures we develop in our laboratory. You can see this is actually flower-like structures we develop. And we can have difference of nanoparticles, as I already showed in our previous slide here, organic, inorganic, polymer based we usually bought from our laboratory. But I asked my students, why don't we make these materials in our laboratory? So we tried with the difference of waste materials. This is one such example you can see here. We use human nail and we make it graphene nanoparticles in our laboratory. And not only with human nail, this you can see we have used chicken feather. So chicken feather we have used. And not only chicken feather, we have used fish scales. Again with the same approach. We have used difference of waste materials and we make a difference of nanostructures, graphene, by using waste materials. And by looking at, for sustainable, composite development or preparation, we are more or less interested in sustainable materials. So rather than carbon or rather than glass fiber or rather than Kevlar fiber, we have done lots of work in that particular area also, and we have published lots in that area. We make composites, but we are more interested in plant fibers. So you can see we have sisal. You can easily extract sisal fiber from sisal plant. You can easily extract hemp fiber from hemp plant, quinoa, pineapple, etc. So this is an easy. It's an easy process. Is very easy to make these fibers. So our approach is making use of these plant fibers instead of glass fiber or instead of Kevlar or instead of glass, instead of carbon fiber. So this is one approach where you can see how we can make plant fiber. See here, you can see this is a Tridas cucumber plant that one can find in our roadside and all. So this is actually the retting machine. So this is the retted fiber, and you can see then we have treated with the alkali, and this is the alkali treated fiber, and this is the untreated fiber. So the process is very easy. So one can make this plant fiber by mechanical retting process. So this is one such example. And if you look at automobile industry or if you look at the aerospace industry, you can see that earlier we are using glass fiber or carbon, glass fiber or carbon fiber we are using. So if you look at Vande Bharat Express, we are using glass fiber. If you look at our buses, transport buses, we are using glass fiber. So you can see we can use plant fiber for making automobile. So we can use plant fiber for making aerospace interior structure instead of carbon fiber as well as glass fiber or even Kevlar fiber. That is the advantage of using plant fiber. So other than microfibers, we are interested with the nanofibers. We make nanocellulose in our laboratory. So you can see some examples here. This is actually the microfiber. You can see the microfiber. We converted it into nanofiber. So the approach is again very simple. So it is actually a three-step process. One is alkali hydrolysis. You can make use of NaOH, KOH, etc. And then you need to bleach it with peroxide. There are different of agents are available. And finally, you can go with acid hydrolysis. So we go with strong acid as well as weak acid. So we have tried different approaches, and we synthesized the difference of nanocellulose. You can see some examples here. So we are interested in nanocellulose rather than microcellulose for making composites. So coming to composites, this is one of our work I have done long back in 2010. If you carefully look at this composite structure, you can see the agglomeration of particles. So why we are interested with the nanocomposites? We want to improve the performance. If you want to improve the performance, you should get good dispersion. So if you have this kind of dispersion, you may not able to get the properties that you want. Maybe definitely the properties will come down. So what we do is, we do chemical treatment. So this is one such approach. So where you can see this is graphene, graphite, and you can see the graphite oxide after some chemical treatment. And this graphite oxide is actually treated with a rubber, liquid rubber, CTBA. And after, you can see a couple of figures here. This is graphene unmodified and this is graphene modified. So you can see the graphene modified is completely covered with the CTBA. So if I put this graphene in polymer matrix, there is a possibility for agglomeration, because van der Waals forces will be there. So because of van der Waals forces, this polymer, this nanomaterials will agglomerate. So in order to overcome this van der Waals forces, what I did is I made a coating of CTBA over the graphene. And now you can see, this is some diamond and XPS, etc. Now you can see the effect here. See here, this is actually the TEM image of the composite. So you can see the agglomeration here. This is untreated sample. This is with the treated graphene, where you can see the excellent dispersion. And you can also see the same in SEM images, where you can see we have excellent wetting here. Here you can see some particles here and there. And this is also reflected in the mechanical properties. And also look at the TG. TG was increased by approximately 20 degrees centigrade. So we have approximate increase, I mean you can see the glass transition increases by 20 degrees centigrade. And you can also measure the interfacial interaction parameter, interfacial attraction, by using this equation. We have 8.84, that is the value we got, that is interfacial interaction for treated sample, treated graphene, but for untreated sample the value is 3.12. So you can have better interaction with your matrix as well as with the particles, with chemical treatment. And other than as I already told, we are more interested in using plant fiber rather than carbon or Kevlar, etc. This is one such example where you can see we have used bio-epoxy resin. So in our laboratory we are interested with bio-epoxy resin rather than synthetic epoxy resin. This is actually bought from France. Approximately 60% is bio-based, 40% is again synthetic. But you can see what we have done is we have used bio-epoxy resin, then we have also used a tribloper polymer. Along with the tribloper polymer, we have used sisal fiber. So sisal fiber is used. And we got excellent properties with this polymer matrix and we have with this material. And this can be used for, semi-structural applications. For semi-structural applications, we can use this kind of polymer composites. Again, you can see this is again another work. Again, you can see this is actually a combination of sisal and temp. In our previous work, we have used the sisal along with the fluoropolymer in epoxy. And here, instead of that sisal, we have used the sisal and temp. That is another approach. Suppose if you want to improve your properties, suppose if your sisal is not giving the right properties, you can combine that sisal with some other plant fiber, such that you can overcome the what. So you can do like that. So you can improve the properties by using plant fiber. Then this is again nanofiber, nanocellulose we made from plant. And then we have used that in starch to improve the properties. See here. And then this is again another one. This plant is actually Cascuta reflex is available all over Bangalore. I have seen in many places. And we have used with the NBR latex. And you can see the improvement in properties here. And then other than composites, we are interested with the flexible epoxies, flexible epoxy. So you can see here, this is flexible. So we make flexible epoxies. So you know that once you completely crossing your thermosetting system, it is hard and brittle. You cannot make it flexible. But we can make it flexible by some adjustments, reduce the glass transition temperature below the room temperature. That is how we make these samples. And this is applicable for automotive as well as flexible and bendable electronics. And we also make conductive flexible films. You can see here, flexible conductive polymer films. You can see the flexible conductive polymer films. And we have used here graphene, and we also use ionic liquid as a dispersing agent. And we make a very nice flexible conductive polymer films. And you can also see the glass transition temperature here. It is approximately 40-45 degrees centigrade. And then we are also interested in shape memory polymers. We publish lots in this particular area. And this kind of shape memory material is widely used for aerospace, for satellite applications. So you can see here, this is actually the permanent shape of the polymer. This is actually what we made, permanent shape. And then what we did is, after some adjustments, what we did is, we heat this polymer above the glass transition temperature. So above the glass transition temperature, automatically our polymer will be flexible. So once it is flexible, you can bend, you can twist, or you can have any shape. See these different shapes, we can have different shape. And after that, and then you cool it, so that this temporary shape will be fixed. And then when you heat it back, it will come back to the permanent shape. That kind of polymer is actually what we call shape memory polymers. So you can see this is the permanent shape, and then you heat above the glass transition temperature. Now it is soft. You turn it, you bend it, you can have any shape. Then you cool it, your temporary shape will be fixed. Then you heat it again, it will come back to the original shape. That kind of polymer is actually what we call shape memory polymers. So I will show you one video here. So you can see this is actually the temporary shape. I am actually adding some hot water, so it will come back to the original shape. So this kind of material is widely used for satellite application. We can save lots of space with this kind of materials. So you can bend or you can twist it, and then once you reach the upper space, you can come back to the original shape. So that kind of application. And then other than that, we are also interested in self-healing materials. Suppose if somebody scratch your car, you need to repaint it. It is expensive. You need to pay 10,000 rupees or 15,000 rupees. So our approach is it should heal permanently without any, without painting, repainting. So this is one approach. This is actually what we call the thermal mending process, thermal mending. So this is actually the polymer coating here. You can see the polymer coating, and you can also see the scratch here. You just heat it above the melting temperature so that the scratch is healed. You can see here. This is actually what we call thermal mending process. And we have done one work we have published one paper in this area. And other than that, this is my student, my PhD student. Now he is in Mahatma Gandhi University. So what we did here, this is another work. So again we scratch, suppose if you scratch your paint, and it should heal in the presence of UV light. So you can see, we made the formulations, and you can see the scratch here. This is nano indentation study. You can see the scratch here. And in the presence of sunlight, you can see the scratch is disappeared. See, the scratch is disappeared in the presence of sunlight. And you can see the mechanism and all. I am not going to explain all these things now. And this is another work. See here, this is actually the polymer material. So we actually cut this polymer material into two pieces, and then we can fix it together. See here, we have already fixed it, and we have also put some weight here, you can see here. So this also we have done with the help of ionic liquid in epoxy, and we are already waiting for the, we published this paper, but the patent we already submitted, filed the patent, but waiting for granting. And other than that, we are interested in lightweight polymer materials. So this is one such example you can see here. This is actually PP-PS blend. You can see the PP matrix and PS droplets over the PP matrix. And after some adjustments, you can see the droplets completely disappeared. See here, the droplet is completely disappeared because of the compatibility. And this is actually also reflected in the performance. See, the tensile elongation is 11%, and it becomes 66%. So we have big improvement in tensile elongation. And this is another work where we have tailoring at the interface. You can see the tailoring effect at the interface. So this kind of tailoring effect at the interface will improve the performance of the polymer. And then you can see another work where you can see the LDP as well as PS. This is actually the blend. You can see both these phases. And also we have incorporated, what we did is we added graphene, and we have used SCBS. And see, we cannot find this phase here. That LDP PS phase is completely disappeared. But you can see nicely distributed graphene platelets there. See there, the nicely distributed graphene platelets you can see, but the phase is disappeared, completely disappeared because of compatibility. And this is also reflected in the performance. The impact strength is 4.5, increases to 60.8. And you can see the tensile strength almost remains the same, but look at the tensile elongation, 3.5 becomes 39.4. And also you can see the tensile toughness, that is 36.5 increases to 573. Huge increase. So you can do magic by changing the parameters. And then not only that, we are interested in food packaging, and this is actually polyvinyl alcohol. So our work is more or less based on bio-based polymers, because synthetic polymers, there is no degradation, and finally it will all deposited in Pacific Ocean. So we have huge mountains of plastics in Pacific Ocean. So we are interested in biodegradable polymers. So in biodegradable polymer, we have used clay as well as lipopeptides. So lipopeptide is actually an antimicrobial agent. So every year, approximately 4.5 lakhs of people are dying because of ready-to-eat food. So many people are dying because of ready-to-eat food. So what we want is, we want to enhance the shelf life of the food material. So this is one such example for that. You can see here, this is actually ginger. This is actually the polyvinyl alcohol film. That is, and this is actually with our modified film. So in PVA, polyvinyl alcohol film, you can see we have that. You can see the fungus there. But see here, we don't have any fungus. So you can improve the shelf life by adding some microbial agents. And this is another work, it is somewhat similar, again with polyvinyl alcohol, but instead of clay, we have used zinc oxide and zinc oxide. And lipopeptide is same. This lipopeptide is actually the microbial agent. So you can improve the shelf life of the food. And this is another work where we have used PHBV, and again there is a biodegradable polymer along with plant natural fiber. But interestingly, what we found is we can improve the shelf life of strawberry. Then this is a review what I wrote, that it is essential oil. Essential oil is another material to improve the shelf life of fruit. So if you use nanomaterials, again, there is a possibility for toxicity that you can avoid with the help of essential oil. This is another work where we have used capsicum oleoresin. This capsicum oleoresin we extract from capsicum, and we have used it with the polymer to improve the shelf life of food materials. And then rather than that, we are also interested in water purification studies, water purification. So water scarcity is actually a big problem all over the world. So we have done lots of work with water purification, and you can see some work here. I'm just skipping it. So anyway, these are my books related to all these topics. You can see some of the books in nanocomposite, some of the books in polymer coatings, some of the books in epoxy, you can see here, and tribology, etc. So these are some of the books we have edited over the last few years. Anyway, thank you very much for your patience here. Clay actually we bought that is more late clay. That is more late. Actually, yeah, that is for better to improve the performance of polyvinyl alcohol. Yeah, improving the strength. That's it. But that lipopeptide is actually that microbial agent, so it can improve the shelf life. Instead of lipopeptide, you can use essential oil. You can use silver nanoparticles, gold nanoparticles, etc. You can use. HND I have used for painting application. No. HND we have used, I will show you. I just skipped that because of lack of time. In this work we have used HND, halloysite nanoclay. So this is actually, we make a polymer coating. Polymer coating, you can see here, we have used halloysite nanoclay, and we have encapsulated this halloysite nanoclay with a bioepoxy resin. And also we have used nanosilica, mesoporous nanosilica, and we have used UV initiator, just to mix it together, so that this UV initiator will somehow enter inside these nanoparticles, nanoclay. I will tell you. Then what we did is, we mixed both this halloysite nanoclay and the silica nanoparticles, encapsulated silica nanoparticles, as well as encapsulated halloysite nanoclay in our paint. And then we coat. Then once somebody is scratched, automatically our halloysite nanoclay will break. Isn't it? Once this halloysite nanoclay will break, this bioepoxy will come out. It will be in touch with our nanosilica, because this is actually UV initiator. Then we have the curing, and we will have excellent healing. So cracks we can heal. Automatically we can heal. You can see here. So this is actually the coating. We have put one scratch here. This is nano intended. But in the presence of UV light, we have complete healing. And this is actually the mechanism. You can see the mechanism here. This is actually the coating. So in this coating, we have halloysite nano tube, as well as our mesoporous silica. And once somebody scratches this, then this halloysite nanoclay will break, and our bioepoxy will come out. No, it will come out and it will be in touch with our mesoporous silica. So in our mesoporous silica, we have the initiator. In the presence of initiator, this bioepoxy resin will cure. That is the mechanism. So we have published this. If you are interested, please have a look at it. UV light triggered cell peeling of the epoxy coating. Last couple of years before. And also I am working here in Alliance University. If anybody is interested to do research in polymer, you can come to our university anytime. I am available 24 hours. And I have published extensively, as you can see. So most welcome for any kind of collaboration. Thank you very much.
plenary speakers coming all the way here and sharing your knowledge with us and enriching with us your research and academic expertise. So that's all for the day. We shall meet tomorrow at 9:30 for the technical sessions.